Thank you all. A very good morning to all speakers, delegates, and student participants, and welcome to the second global webinar on applied science, engineering, and technology, organized by the Global Scientific Guild. I am Professor Ranganathan from the University of Tours in France. Tours is in the center of France, about 240 kilometers south of Paris. I'm an emeritus professor at the University of Tours, and my field is material science, fatigue and fracture mechanics. I have published more than 120 papers in scientific reviews and brought out 6 or 7 books. I don't remember the number. Okay. On behalf of the organizing committee, it gives me great pleasure to welcome you all to this international conference. I thank you all for attending the conference today. Today marks an enormous event initiated by the Global Scientific Guild, which will provide the opportunity to share research findings and encourage new collaborations to interact in various areas of applied science, engineering, and technology. The second global webinar on applied science is a scientific congregation that brings together researchers, scientists, key decision makers, industry professionals, the same physical space for a brief yet intense period of discussion, collaboration, and generation of innovative solutions to address overreaching challenges related to the theme modern trends in applied science and engineering, progress to the future. We are pleased to welcome you to both share and witness advances in this field together. The conference has attracted speakers and delegates from all over the world. I would like to thank all speakers and event partners for their continuous support and patronage. The Global Scientific Guild also wishes to thank all the organizing committee members who have put in long hours and generated many creative ideas to bring this meeting together. They have received 46 abstracts and 23 were accepted. The speakers are from 12 countries. Finally, we thank each and every one of you, the participants at this conference. We hope you enjoyed the conference and your participation will lead to new ideas, collaborations, and research initiative. Thank you. Have a good conference.
Thank you, Professor Ranganathan, for the introduction speech. Let's begin the talks now. Our first speaker is Professor Ranganathan. He's going to give the presentation on the energy-based approach to fatigue. And I request Professor Ranganathan to start his presentation.
So good morning again. So the title of my talk is the energy-based approach to fatigue. The different topics which I'll treat are fatigue crack initiation in metals, notch fatigue, multi-axial fatigue, fatigue crack propagation, and fatigue of elastomers. So when you look at metals, the process of fatigue is quite complicated. Imagine a metallic material with lots of grains, which has been subjected to fatigue loading, okay, in a vertical direction. The initial stages of fatigue is creation of intrusions and extrusions that leads to surface roughening. This will lead to a small micro crack inside the first grain. This will be along the grain slip planes. Then it can go to a second grain, still along slip planes. Once it has traversed 2 or 3 grains, it becomes a stage 2 fatigue crack, which grows to failure. So you have different stages of fatigue. So there's different models have been proposed to understand the fatigue crack initiation process. One of the models is the one by Tanaka and Mura. The number of cycles of fatigue crack initiation is related to the Ws energy to create a surface, the shear modulus, okay, and the dislocation size, and the back energy. So this can be a model that can be fitted to um, develop the number of cycles to fatigue crack initiation. At more direct applications, the Halford's law, which represents the low cycle fatigue behavior of metals, which says that we correlate the number of cycles to failure to the energy dissipated per cycles, and theta is a material constant. So this has been applied by one of my students to the fatigue of um, a material which is used in solders, and these are the fitted laws to the experimental data. Now let's move on to the fatigue crack initiation at a notch. This was developed by Professor Glinka from the University of Waterloo. It's an energy-based model. So the idea is to say that when you have a notch, you have an elastic plastic field, while the global field is in the elastic regime. And when the global field is in the elastic regime, the local field is governed by the same amount of energy dissipated. From that, these two equations have been developed. KT is the stress concentration factor. Delta sigma infinity is the load stress applied at infinity, and sigma and epsilon are the local stresses and strains. So these two equations have to be solved. It is numerically solved to get the local stresses and strains. Once you get the local stress and strains, you can correlate that to the initiation life. So this we have created a short crack model. I won't go through the details, okay? In this short crack model, the crack initiation life is the number of cycles necessary for the crack to small crack to obtain a detectable length. Okay, so these are verifications using notch specimens in the 2024 aluminum, copper, magnesium alloy. Crack length versus the number of cycles. You can have different configurations. You can have a true thickness crack or a corner crack. So this is the crack growth compared to the stress intensity factor. This is the long crack behavior. This is the short crack behavior. So this was measured by scanning electron microscopy photographs. So you can find that the correlation is acceptable. Then we did also variable amplitude tests. This was twist is an aircraft wing loading spectrum. We extracted one flight from that. So this is the load variations during the 500 cycles. Okay, and this was applied, and we measured the number of cycles of crack initiation. So this is the comparison of different models. Maximum stress to crack initiation life. We have the experimental data. These are the rounds here. Okay. You have the Morose models, Smith, Watson, Topper, and the short crack model which we developed. Okay. The short crack model seems to be slightly underestimate the fatigue life. Okay. And the short crack model, you can give scatter band for the life depending upon the initiation crack size. So it is quite acceptable because it is a number of flights of 100,000 flights means about 226 million cycles applied to the specimen. So you get a very good prediction, which is not bad at all in the case of fatigue situation. Then we'll move on to multi-axial fatigue. I'm sorry, I'm treating so many different topics. because this is just to show the versatility of the energy-based approach. This was developed by Garud and Yahed in 2007. So in this, total energy per cycle is the sum of energy in the tension compression direction and one in the torsion fatigue. Okay. So you have axial elastic energy. It was separated into different parts, elastic and plastic energies. Okay. And then the correlation between the energy and the number of cycles of crack initiation. And the number of cycles to failure in a multi-axial fatigue situation is the ratio is taken as a minus sum of the axial energy, ratio of the axial energy to the total energy, and the ratio of the torsion energy, the total energy. Okay. So these are the different materials studied. AIS, American AISI 304 steel, chrome molybdenum vanadium steel, aluminum alloy 7075 T6, Haynes alloy. So the different, even the Inconel 718, these are all very used in high temperature situation. And the different loading condition studies is it's quite complicated. Tension fatigue, torsion fatigue, proportional loading, biaxial tension, etc. And in phase and outer phase loading. And you get to 147 different data points representing these loading situation. And for these different materials, here you have the predicted life versus experimental life. You see that this, within a scatter of 20%, all these data are within the scatter, which is extremely acceptable in fatigue situation. Now let's go to fatigue crack propagation. So initially, Paul Paris, he passed away 2 years ago, developed the crack driving force delta K. Then Elber modified it to introduce the crack closure concept. But the difficulty about crack closure is that there are different causes of closure identified, like plasticity, roughness, mixed fold crack opening, oxide induced, etc. So it's quite a complex situation. So what I'll now talk about the energy-based concept, which is based on the Griffith concept developed in 1920. In 1973, Johannes Wertmann proposed this crack growth law. dA over dN crack growth rate is proportional delta K power 4 divided by shear modulus, the flow stress squared, and the energy to create a new surface. Now, this energy to create a new surface is different from energy to separate the atoms, because it is energy to separate the atom theoretically is quite low. But for ductile materials, you have to add the dissipation of energy in the plastic zone. So the U is plastic energy plus gamma for ductile materials. There are different methods to measure this U. I developed a simple method based on crack opening displacement gauge in 1985. So we'll now compare and discuss the two approaches, crack closure and the energy-based approach in the 2024 T351 alloy using compact tension specimens in overload and variable amplitude tests. So this is the specimen, okay? It has been modified to measure the energy under, this is the loading line, okay? This has been modified to measure the energy under the loading line, okay? You don't have any spurious measurements of energy. So if you look at the load versus displacement diagram, this is the load versus displacement diagram. This is amplified and corrected for crack closure. I mean, a part of crack closure. And at the same, so if you take this this concept, in here, the compliance is the highest. And when you come to the low loads, the compliance is increasing, which shows that the crack opening load is defined somewhere over here. But at the same time, if you look at the DC potential drop, you find that even after this load, you have some potential drop variation. So it's very difficult to identify without ambiguity what exactly is the closure. Now let's look at data now. This is crack growth rate versus stress intensity factor amplitude for 5 different load ratios. And this was a project which I did with the Airbus Industries in the 1980s. Okay, this is the same data corrected for crack closure. If you accept a scatter of 10, okay, so you can say that the crack closure model is applicable. Now let's look at the energy-based approach. This crack advance per cycle versus energy dissipated per cycle. What you find here, two different regimes. At high growth rates, we have a linear law correlating these two parameters. Where at low grade, you have power law relationship. Okay? Similar results with acceptable scatter. Let's see what happens after an overload. An overload is what you do is you create a crack at constant amplitude cycling and you apply an overload and you come back to the previous loading. When you do that, the crack, this is the initial crack growth rate. You apply the overload here, there's a small crack acceleration. Then it decelerates to a minimum growth rate and start reaccelerating. Okay. So in this case, if we look at the crack growth rate versus the effective stress intensity factor corrected for closure, you find this kind of a behavior. You don't have a single relationship and you have lots of scatter. Because what happens is it's difficult to measure closure in this situation. You can either measure closure over here, no closure at all, or a closure at a very high load level. So it's a complicated situation. While if we look at the energy dissipated, it's more coherent, which I'll show it to you. So this is the crack growth rate versus the energy parameters. See, the energy dissipated per cycle. When the cracks are decelerating, the energy decreases here, and the crack is accelerating, it starts increasing. So if you know, compare crack advance per cycle to the energy-based approach, for constant amplitude and overload tests, if you have a single law extending over 7 decades of growth rate, which is extremely interesting. Now we can now move to more complicated loading situation. You can have a block loading. There are four different load levels, mean levels, and this block is applied. And you look at this is a simplification of the aircraft wing loading spectrum. Okay. So if you look at now, you can look at the load versus displacement amplified to measure the energies. Okay. So this is the stress intensity factor approach. In this case, you have the crack advance per cycle with respect to K max during a block. Okay. And you find that for each loading situation, A, B, C, and D, for each blocks, you have a different crack growth law. While in case of in the energy-based approach, crack advance per block versus total energy, you get the previous linear law for constant amplitude situation is again found here, where at low growth rate, you may have a power law relationship. So it's much more coherent with respect to the crack closure. Now, are these approaches really different? This is an experiment which I did long time back. I started with the annealed alloy, okay, and applied an overload, and the crack grows to the lowest growth rates. Here, what we do is we re-anneal here. The residual stresses at the plastic zone are removed, and when we restart the cycling here, you find that immediately the crack goes over here, crack growth rate. That is the closure decreases, energy increases, and crack growth rate increases. So that means this energy and closure, we talk of the same physical processes So they're quite compatible. Now we come to the final topic. Please tell me how much time do I have? Okay. This is the fatigue of chloroplane rubber using dumbbell specimens. Okay. This is a project we had with the Hutchinson Industries. So these are the details of the materials. Okay. They have 50 PHR charges and plastic iron. I mean, these are nomenclature used by the rubber industry. So this elongation to failure 680%. So it's a typical rubber material. So we did fatigue tests in different conditions. First of all, we wanted to know which is the mechanical parameter governing fatigue. This is strain amplitude. Okay. Strain amplitude is the number of cycles to failure. Or is it the stress amplitude? Okay. These two are second order tensors. Okay. Or the energy dissipated per cycle. Okay. In fact, you can take either of these parameters, but we will look at more at the energy based approach. Okay. So these are quite acceptable, either of these parameters. The advantage of this energy is that energy is a scalar. For instance, if you take the effect of frequency, let's say 5 hertz, 20 hertz, and 30 hertz, you get three different curves, and in terms of energy, you get you need only just one curve representing energy to number of cycles to failure. So energy is an acceptable parameter. It's a scalar. It takes into account frequency effect and the load ratio effect. I won't talk of that today. Now let's look at some more complex situation which represents biaxial fatigue. Okay. So we did the tests at different load ratios, minus 0.3 to 0.5, biaxial tension fatigue, tension torsion, with different values of dephasage, phase relationship, okay, and different values of displacement ratios. So this is the phase difference between the axial and torsional loadings. You can have different phase angles as we saw for the metallic tests a few minutes back. Now we did a constitutive modeling. So it's a hyperelastic material. We use a Mooney-Rivlin model with two invariants, okay, with the dissipative part, and we identified the model parameters. If you compare the model area and the experimental cycle, it's quite acceptable. So we have the constant for the Mooney-Rivlin relationship. Then we look at the dissipated energy density, first principle stress, and the strain energy density as different parameters. Okay. So we develop the Hay diagram, which describes the constant life diagrams for materials with respect to load amplitude and mean load. Okay. What happens is that these rubbers have a very peculiar properties. Some of the materials can crystallize during fatigue loading. Okay. So that means that the resistance will increase. In the case of non-crystallizable rubbers, like the SBR rubber, so there's a decreasing relationship here. In the case of crystallizable rubbers, like the natural rubber, you have two slope variations here, a slope variation. So this is the region of crystallization. So we didn't know about our chloroplane rubber, if it can crystallize or not. So from our test, what we found was, this is fatigue lives index in 10 power 5 cycles, okay, you find that this rubber is crystallizable, okay, with the two slopes identified stress amplitude as a mean stress diagrams. So let's look at the different models. First principle stress pK1, okay, the correlation coefficient is 0.51, which is quite bad. The global strain energy, it increases 0.58, slightly better, okay. The local dissipated strain energy, which is a better correlation factor, okay. The final one is the global dissipated energy density with even slightly better correlation coefficient. So we can compare end of life cycles from the model data and experimental data, and it's you get a very good correlation. So the main conclusions are the energy bundles are very efficient in most fatigue situations, crack initiation, notch fatigue, multi-axial fatigue, fatigue crack propagation, and elastomer fatigue in uniaxial and multi-axial situation. Thank you very much.
Our next speaker is Professor Shigo Akashi from Tokyo University of Science, Japan, and he is going to give a presentation on network theoretic classification of cyber attacks and its application to preventing outbreak of potential attacks. And I request Professor Akashi to start his presentation.
Thank you so much for your kind introduction. Could you please make my screen shared with all participants? Okay.
Yes.
Okay. First of all, I would like to express my hearty gratitude for all the participants and Professor Rangana-san and Professor Raj and all the other members of the local organizing committee who are having given the chance of my talk today. Thank you so much. First of all, could you please kindly remember this word? Network routing indicating packet transmission routes can be intentionally changed from the outside of the internet, regardless of whether the change has performed intentionally or not intentionally. Okay. Now, first of all, I would like to demonstrate some sample program. Okay. From now on, I would like to introduce two official websites. One is especially prepared for my university. This is my my university's website written in English, Tokyo University of Science. And the other website can be seen like this way. This is the most largest karate teaching association. When I was young, I studied karate a little, okay? But as we see, these two websites have no relation between each other, of course. So, could you please remember, I would like to say again, these two official websites, okay? Now, this is a virtual, okay, sorry. This one, this one, this one. This is a screen, especially used by me for my private life. This monitor is now presenting the email list, having reached me. And this is email, okay, composed by me. Sorry. Oh, okay. Okay, as we see, as we have seen, this URL is especially assigned for my university. I told, okay, a few minutes ago, okay? Then, exactly speaking, please, sorry, what? Sorry. This is a real-time simulation experiment. So I don't know. I cannot predict what will happen for disturbing my speech. I'm very, very sorry. Okay. As we have seen, this is especially assigned for my university's official website. And I will click now. Now loading. And I have succeeded in obtaining the other result. This is especially this is the official website, especially assigned for the largest Japanese karate teaching association, whose name is exactly Nihon Karate Kyokai. So I clicked this one. Okay, this is the another official website, especially assigned for Niigata University. I would like to click here. Please kindly watch my performance. Oh, the same website has been obtained by my performance. Please kindly remember this virtual malicious email has been composed by me. But this is nothing but the proof of the performance which enables all the packet streaming on the internet to be changed maliciously. This is the reason why. Then I would like to move the another, okay, performance. Now, I would like to present the simplest structure of bringing about the packet oscillation artificially, not spontaneously, but artificially. So this structure is so simple. As we see, there are 3 network segments on this map, okay? The left-hand side network segment is encircled in blue. And the right-hand side network segment, thank you so much for your kind advice. I really appreciate every time. Okay, Okay, as we see, this is the structure. This figure shows that the simplest structure for bringing about the packet oscillation artificially, not spontaneously. So this is so simple. As this map shows, there exist three network components on this map. The left-hand side network segment is located, is encircled in blue. And the right-hand side network segment is encircled in pink. And the intermediate network segment is encircled in yellow. Okay, this is yellow encircled network will become a victim of the cyber attacks, which we will see later. Okay, now we assume that the user of this left-hand side PC will send the ICMP packet originating in this PC, which is bound for the right-hand side web server, which is located on my right-hand side. Okay, could you please kindly remember the computer theoretic address, which is called IP address? As for the left-hand side PC, 192.168.0.2. And as for the right-hand side PC, and as for the right-hand side web server, 192.168.2.2 has already been assigned. Okay. The normal, before introducing the malicious behavior, we would like to introduce a normal packet transmission. This is experimental result. Okay. Exactly. In other words, this figure shows that the ICMP packet, which is originating in 192.168.2.2, which is assigned for the left-hand side PC and is bound for this one, 192.168.2.2, which is especially assigned for the right-hand side web server. Only three logs have already been caught by this system. Okay. By the way, this is the malicious result. Okay. Okay. If the left-hand side PC user send the packet which is bound for this IP address, 192.168.23.2, there does not exist any PC having this IP address. There does not exist any PC or any router having such a kind of IP address, 192.168.3.2. This packet sending has brought about such a tremendous oscillation of packets. Okay, as we see, only one packet which has already been malicious from the left-hand side PC user has been oscillating between the intermediate network segment located between the left-hand side and the right-hand side. Exactly speaking, this packet is oscillating between this router and this router, like this way. Now, we would like to introduce the difference between server targeting attacks and bottlenecked link targeting attacks. Exactly speaking, by using our modern contemporary network skills, server targeting attacks can be protected to some extent. But unfortunately, bottlenecked link targeting attacks cannot be removed from our internet society. Unfortunately, this is the exact reason why I would like to mention the difference of the server targeting attacks and the bottlenecked link targeting attacks. There exist two maps. On this figure. Okay, as we see, there are 7 malicious PC attackers on this map. 1, 2, 3, 4, 5, 6, 7. And there are 3 web servers located on the right hand side. 1, 2, 3. And the group consisting of these 7 malicious attackers and the group consisting of 3 web servers are connected through the internet. This is a normal case. Perhaps if we look at these 2 pictures, these 2 maps are like the other. As exactly speaking, the left-hand side located map is very similar with the right-hand side one, as we see. But what is the difference between these 2 figures? Okay, exactly speaking, the answer is the following. These 7 malicious attackers give offense to the web server. Exactly speaking, the intermediate server, they give offense directly to this intermediate server. So even if this intermediate server has been made down, the other 2 servers can continue to offer their service. This is the reason why the damage is not so huge. I would like to say again, even if this intermediate server has been made down, the other 2 web servers located upside and located downside can continue their service. While the previous case, the right-hand side case is more malicious because these 7 malicious attackers give offense to this bottlenecked link. If this bottlenecked link has made down, none of these 3 servers can connect themselves to the internet. So no service can be offered by this group. This comparison of the left-hand side picture with the right-hand side picture can conclude the following result. The network segments suffering from the other bottlenecked link targeting attacks are geographically wider than those suffering from the server targeting attacks. I would like to say again, the network segment suffering from the bottlenecked link targeting attacks are geographically wider than those suffering from the server targeting attacks. As we see, on the left-hand side, only 1 server has been made down. In spite of that, on the right-hand side picture, all the 3 servers has been made down. This example can prove this result. Now, I would like to compare the routing loop and the packet oscillation. As I told previously, routing loop can be we can prevent routing loop. We can prevent our network from occurring the routing loops by using the contemporary network skills. This can be protected by the modern network skills. In spite of that, the packet oscillation cannot be removed in our modern network society. As we see, there exist 3 routers on this map. Okay, these 3 routers are connected to the other 2 routers with each other. Okay, then if the routing loop has occurred, unnecessary packets will travel around this triangle, go along with the network cable like this way, clockwise or counterclockwise. In spite of that, the structure of packet oscillation is the following. Exactly speaking, the network area ranging from the damaged segment is so small in comparison with the damage in comparison with the physical area of network. But the damage is so high, exactly speaking, higher than the other, this one, okay? The packet oscillation is the following. Unnecessary packets commutes between this router and this router. As we see, oscillate between this router and this router. And some other day, another packet oscillation may occur on this network segment. So while packet oscillation occurs, we cannot use this network link. So we must use the other 2 links. So then, exactly speaking, this inconvenience concludes that when the router 3, this one, want to communicate with router 2, he cannot use this network segment. So the router 3 must send his packet by way of router 4, like this way. So the 2, exactly speaking, 2 packet oscillations occur simultaneously. For example, this one and this one. For example, we assume that the 2 packet oscillation occurs this one and this one. The router R2 pointed by me, this one, will become isolated from the other. This consideration will conclude the following. Is it possible for packets to oscillate between the end of a link and the other one? The answer is affirmative. Packet oscillations are different from the other routing loops. I would like to say again. The routing loops can be removed by the modern network skills, but packet bottlenecked link cyber attacks cannot be removed up to now. The second result is the following. Modern dynamic routing protocols, I would like to say again, may not be able to perhaps I think. So there exists some small examples. May not be able to protect bottlenecked link targeting attacks. Now, we would like to demonstrate by the simulation software developed by Cisco Networking Academy. This is a very simple model, but rather more practical than the previously mentioned one. Okay. As we see, there exist main three network segments. The first network segment is encircled in blue, and the other network, the right-hand side located network segment, which is located below, is encircled in pink. And the bottlenecked link is the following, encircled in yellow. And before presenting the malicious packet oscillation, I would like to show you all the normal and authenticated communication between this one and this one. And the sequential record can be exactly recorded by this packet sniffer. Could you please wait a moment? Okay. From now on, I would like to send, sorry. Excuse me, how long is it remain? How long does it remain for my talk? Can you hear me?
Oh, yes.
How long does it remain for my talk?
Still there are 10-15 minutes you can talk.
Thank you so much. I have been so relieved to hear that. Okay. I would like to send 4 packets from here. We sent just 4 packets. And this packet sniffer recorded the 4 packet has exactly reached. I would like to play again. This is a normal way of packet communication. Okay. Then now I would like to show the packet oscillation. This is intentional one. Okay, like this way. Could you please kindly the sequential behavior of these packet sniffers? The left-hand side screen is for the sniffer for download streaming. And the other screen is especially prepared for the upload streaming. By using these 2 screens simultaneously, we can gather the packet streaming from up to down and from down to up simultaneously. Here, we would like to use this malicious router. Okay. I'm ready for this performance now. This is the sequential behavior showing the packet oscillation. Only 5 packets communicate between the yellow colored bottlenecked link, which I have told. Still communicating between the upward and the downward. Oh, finished. This is nothing but the magnification of 5 packets, exactly speaking. Then has only 5 packets has been magnified. Too many unnecessary packets, and all of unnecessary packets communicate between this bottlenecked link. While the packet oscillation is occurring, these two PC, this PC and this PC, cannot connect themselves directly to this ISP router. Now, we would like to summarize the comparison of server targeting attacks with bottlenecked link attacks. The most important point is the following. The server targeting attacks is also so famous. But if we compare this attack with the bottlenecked link attack, this packet oscillation, bottlenecked link cyber attacks seems to be potential. But once this attack happened, the damage is very, very huge in comparison with the damage brought about server targeting attacks. Thank you so much for your kind attention.
Our next speaker is Professor Jc Umavati from Gulbarga University, India. And I request Professor Umavati to start her presentation.
Can you see my slides, Nawash?
Yes, yes, yes.
Oh, yeah. Okay. Good afternoon to Professor Ranganathan and Professor Shikao, and I thank the organizers for including me in this conference and also giving me the opportunity to present my work. So the title of my talk is Computation of Combined Electrical and Magnetic Field Effects on Dissipating Immiscible Newtonian fluid or the nanofluid dynamics. A brief abstract of my work is I'm going to present the numerical simulations for nonlinear mixed convection heat transfer in an enclosure where we divide that into two different regions. One is conducting and another one is non-conducting. So whenever you have two immiscible fluids, naturally there is an occurrence of interfacial, and an interfacial stress condition is also employed at the junction between the two immiscible fluid zones. I'm also considering the nanofluid, electrically conducting the fluid which is saturated with nanoparticles. And who are working in the field of nanofluids, we know there are two big different approaches. One, we follow the Bongiorno's model, or we follow the Tiwari-Das model. I will not go in detail about the models. So here at present, I'm using the Tiwari-Das nanoparticle fraction model. And the coupled equations are made dimensionless and solved numerically using a finite difference method, adopting the Southwell over-relaxation method subject to appropriate boundary and interface conditions. The major contribution or the application areas of this type of work is in nano-doped electromagnetic hybrid fuel cells, medical flow processing also, that is electromagnetic blood flow meters, and also we can use in sensing systems in chemical engineering and a lot of other applications. Just brief introduction before going for the formulation and the analysis. Thermal transport phenomena in which both forced convection and free convection exist simultaneously is known as mixed convection flows. Such flows are found in thermocapillary systems, propulsion of hydrophobic particles in phase change gels, multi-phase droplet combustion in rocket fuels, and also in stratified atmospheric fluid dynamics, thermal plumes in geophysics, etc. Mixed convection, it consists of both external and internal flows. It can be laminar, transitional, and also turbulent. The mixed convection arises when the inertia and buoyancy forces are either parallel or perpendicular to each other. So if they are parallel, we call that as a free convection. If they are perpendicular, we call that as a forced convection. So mixed convection flow embedded in a rectangular duct. We have ample of geometries. In particular, I have chosen a rectangular duct, which was first inspired by Barletta. He is an eminent professor in north of Italy. Then in modern industrial energy and biomedical applications, both electrohydrodynamics and magnohydrodynamics have emerged as a significant areas of interest. As we know that magnetic therapy is also one of the major treatment in the joint pains and all those things. So electrofluid dynamics also features in numerous energy systems and medical techniques and enables substantial manipulation of fluid phenomena. A lot of literature is also found in, and major citations which I have to mention is about the immiscible fluids. So we find the heat transfer or mass transport of the electrically conducting nanofluid in one fluid model. In one fluid model, I mean to say that they consider only either water or blood or ethanol glycol or any one fluid. But here in my analysis, I am considering not only one fluid, but the two fluids which are not mixing to each other. They are immiscible, like kerosene and water. If you take kerosene and water, they are not miscible fluids. So such applications are abundant in nature, especially when you go for the Earth's core. We find such combinations of fluids, especially if you are aware with extraction of crude oil, extraction of petroleum, so many things are there in the nature itself. So above studies generally were restricted to single fluid. So my work is concentrated on two fluids. Of course, we can do it for 2 or 3 or multi-fluid flows also. So the major challenging problem comes is when we consider the multifluids, the problem arises due to the interfacial conditions. How to define the flow characteristics at the interface is a challenging problem. This is not the recent problem. Since long back, people are working on immiscible fluids, but still we are unable to actually predict the exact flow structure for immiscible fluids. However, we are a little bit capable of getting some of the basic results by incorporating few of the what I can say, some assumptions. So few assumptions basically were given by Beckerman et al., where he takes the porous and fluid layer, and even the height of the two fluids is also equally important. So regarding the length of the two fluids, how to consider the length of the two fluids was advised by Kimura et al. Of course, myself and Malchetti, who is my research supervisor, we are working on two immiscible fluids way back since 1996 onwards. So now my particular work is now related to with the same work which we have done earlier, but by adding the nanoparticles. So in 1996 only, in the International Journal of Nonlinear Mechanics, I have worked on electrically conducting fluid for one fluid model. But now I have improved there. I took a channel only, but now I'm considering the duct, which is more suitable for practical applications. So using nanofluids, we know very well that the thermal conductivity can be enhanced, and also we can control the heat transfer with the nanofluids. It's not only that we can improve the thermal conductivity, depending on the choice of the particles, we can even reduce the heat transfer. So people have the notion that if you use nanofluid, thermal conductivity is always increasing. No, it's not that. It's not that way. So electromagnetic nanofluids, the applications of electromagnetic nanofluid dynamics grown in the areas of given by Jahu and also by Fatima. Jahu is more interested in heat mass transfer, whereas Fatima, the work is concentrated more on medical field, like super paramagnetic doping of tissue in laser, hypothermia treatment, even joint pains, we give magnetotherapy. So now electron nanofluid flow studies include, these are all only magnetic fluids, but now including electron nanofluid. That means apart from the magnetic effects, we also give some electric power. So electron nanofluid flow studies include recent analysis by Prakash, and also using metallic nanoparticles in electrokinetic peristaltic pumping in microconduits. Peristaltic flows also people are studying using electromagnetic theory. So inspection of the literature has identified that there is an absence of studies. As I already explained you, these studies are made only for one fluid model, but the motivation of this work is to consider the electromagnetohydrodynamic convection adopting nanofluids in Coliseum replated with two immiscible fluids. So this is the focus of the work. So here I have used the Tiwari-Das model, and I have also used different base fluids, water, blood, and engine oil, with different combinations of nanoparticles such as copper oxide, aluminum oxide, and graphite. These are only some examples. Actually, this paper is related with the mathematical modeling for a general. That means we can, using this model, we can take any base fluid and any combination of nanoparticles. It is not restricted, but just for the presentation, I have chosen these things. So let us start with the geometry of the model. As you can see that we have a duct. In the duct, we are filling two immiscible fluids. It should be two immiscible fluids. That should be the combination which is very much essential for this model. So we fill the duct with two immiscible fluids. Let us denote that the interface, the line of interface as above the line of interface denoted by zone 1, below the line of interface denoted by zone 2. So zone 1, I'm considering purely viscous fluid, whereas zone 2, here also it is viscous fluid only, but that fluid is electrically conducting and it is saturated with nanoparticles. So left and right plates of the walls of the duct are heated at TW2 and TW1 respectively, such a way that I'm considering heating at the right wall and cooling at the left wall. That means TW2 is greater than TW1. The width of the duct is considered to be B, and the length of zone 1 and zone 2, the total length, I have considered it as A, and I'm considering the interface exactly in the middle of the duct. So the height of the zone 1 will be A of 1 by 2, and the height of the zone 2 will be A of 2. Here superscripts 1 and 2 represent for zone 1 and zone 2. Further, we are considering isoflux conditions. That means dou T by dou X equals to 0 and dou T by both at the top and bottom. That means flux conditions means there is no heat transfer. So this is the configuration of the model. We will, as usual, about the formulation using the Navier-Stokes equations. For this model, zone 1 and zone 2. Since we are considering two different fluids, we have to consider the velocity, the physical properties completely different. We have to define completely different physical properties, such as I'm considering let mu of 1 be the viscosity, rho of 1 be the density, beta of 1 be the thermal conductivity of zone 1. Similarly, mu of 2, beta of 2, rho of 2 to be the physical properties of zone 2. Zone 1, I'm filling with a purely Newtonian fluid. So this is your first equation is your conservation. Second one is your energy equation. As everybody knows that mu contributes for the viscous effects, and rho g beta contributes for the buoyancy forces. Similarly, in the energy equation, dou square T by dou X square contributes for the thermal conductivity effects, and the third term contributes for the what I can say viscous dissipation effects. Since we are considering in zone 2 a fluid which is not miscible with the fluid filled in zone 1, so here not only the regular fluid I'm considering, I'm also adding some nanoparticles. So let us distinguish between the fluid and nanofluid by the notations NF and F. NF stands for the nanofluid and F stands for the regular fluid. So these are the balance equations for electrical conducting fluids. And I'm considering the reference temperature to be the average temperature. Average temperature, I mean to say that take the half value of TW2 minus TW1 divided by 2. Let us have that in exactly which comes in the center of the duct. So the convection is due to, because we are including the buoyancy forces, so it is obviously due to the temperature differences. And also we are including no slip conditions on the periphery. Periphery means on all the boundaries of the duct, the velocity is 0. That means I'm going to consider the rigid surface. Rigid surface. So the no slip condition, and at the interface, as I already told, this is a challenging problem. So it's very difficult to understand what is the continuum mechanics that exists between the two layers. So in the literature, when we consider, of course, if you see the literature, people have worked a lot on the interfacial conditions. You have some 6 to 7 different types of interfacial conditions. So still it is a biased one, which is a more suitable interfacial condition. But at present, I'm using Beckerman et al. Because he has proved that using his assumptions, it is little bit closer to the experiment, but they are not the granted or taken into consideration still research is going on, the interfacial conditions. So let us understand, as you know that if you see the figure, now we have to understand how many boundaries are there, how many interfaces are there. So here you can see that top and bottom are two boundaries, left and right are again two boundaries, where we have bifurcated into zone 1 and zone 2. So in total, we have boundaries to be 1, 2, 3, 4, 5, 6 on the peripheral, and one more at the interface. So 7 conditions are there. But what is the order of the equation we have? In total, we have 2, 2, 4, 6, 8 conditions. So we require for the existence of the solutions 8 conditions. So what are those conditions? As usual, no slip at the boundaries. That means 1, 2, 3, 4 on the velocity, and TW1 and TW2 on the right plate and left plate contribute for the boundaries. And the remaining, in order to match with the remaining order, actually we need 8 conditions. So that we satisfy, assuming the shear stress at the interface. That is continuity of velocity and continuity of shear stress for the velocity, continuity of temperature, and continuity of heat flux at the interface. This assumption is given by Beckham and et al. So in order to satisfy this condition, one needs to have continuity of velocity. Means here when the system must and should have always this condition should be satisfied. That means whatever may be the flow, when the point reaches, when the fluid particle reaches at the interface, the velocity of the upper zone and lower zone, they must be equal. I don't know how far experimentally this will be satisfied. I myself not happy with this condition, because this is when we go for turbulent, these things will not satisfy automatically. But however, my problem, I have considered it to be laminar. But in spite of that, even if it is laminar, how one can control the flow, satisfying that velocity is always equal? It's a $1 million question to me. But something we can understand the flow structure, assuming these properties. So continuity of velocity, continuity of temperature, continuity of shear stress, and continuity of heat flux. So these are the important things whoever is interested in discussing or working with the immiscible fluids. Next, we go for the, as usual, classical procedure of solving the Navier-Stokes equations, balance equations through non-dimensionalization. Everybody knows the reason why we have to do the dimensionless analysis, so that when we do, it will not change any of the physics or nothing else. It is only for the purpose of computation. So when we do dimensionless, we get a frame of reference where all the units are 1. That's the main intention. So that analysis will be more, what I can say, it will be like a model. So people working in fluid mechanics know very well about the dimensional analysis, how we reduce using Buckingham-Pi theorem, how we get the dimensionless parameters, how to reduce if they are 6, how it comes to 4. Those things I will not enter into the things, but who are interested, just it is a guideline that you read Buckingham-Pi theorem, you will understand the purpose of using the non-dimensionalization. So after doing the non-dimensionalization, what are the dimensionless parameters we have obtained for the for this type of equations are as usual Grashev number and Brinkman number. Grashev number is the contribution of buoyancy forces, and Brinkman number is the contribution for the viscous dissipation terms. So go for the zone 2. Here we observe that apart from Grashof number and Brinkman number, we have Hartmann number and also capital M and also capital E contributes for your electric field load parameter. Apart from that, we have some notations such as beta, lambda, n, sigma nf, sigma f. As I already told, sigma nf stands for the nanofluid and sigma f stands for the base fluid. So during non-dimensionalization, we must always keep in mind that we should always go for keeping the reference to be a fluid. Hence, we get ratios. So beta stands for beta nf divided by beta f. Lambda stands for mu nf by mu f. So during calculations, we come all these mathematics. So it's not a big deal. Xi stands for the ratio of KNF over KF. So the dimensionless boundary and interfacial conditions are defined as follows. And we go for the solutions of the obtained equations. One can observe that these equations are partial differential equations. Not only partial, they are coupled because of buoyancy effects also. It is not possible to find out. Of course, the special cases can be found because when you take Grashof number 0 and Brinkman number 0, they reduce us to Laplacian and the solutions can be obtained. But that will not serve our purpose. So we have to include the Brinkman number and also the Grashof number and also the Hartmann number and electrical load parameter. So analytical solutions are not possible, and approximate analytical solutions are also can be tried maybe with the help of a HAM, that is Hamilton method, or you can also go for DTM, that is a differential transform method. But I don't know, DTM did not work for this geometry. Because maybe the reason is that when I take positive values, I'm getting the DTM solutions. But when I take negative values, the DTM solutions are not matching. Maybe because while applying the DTM method, we are using the Taylor series expansion. And Taylor series expansion is a squaring, cubing, fourth order terms. So maybe because of that reason. But till today, I have not found any paper solved using DTM in spite of me trying also. So I don't know the reason for that. Maybe as I explained that when we are using differential transform method, the sign, the rotation cannot be attained using the series solutions. So that's why I used the good old numerical method, that is finite difference method, and along with the Southwell over relaxation method, because when we use Southwell, it is always convergent. But of course, for our particular problem, we have to go for convergency analysis and all those things. That is always there. But normally, Southwell over relaxation is always stable. If you read the stability analysis of Southwell over relaxation, there are some conditions where if we adopt Southwell, the system is always stable. So who are working in finite difference method, I need not explain. We have to take the length of the grid, width of the, because it is partial differential. So we have to generate the grid both along X and Y directions. So along X, delta X and delta Y, NX and NY are the length of each grid that I have chosen. As we know very well that compared to forward and backward finite differences, central difference is more, order of error is less there. In forward, we get order of epsilon, whereas in central, we get order of epsilon square. So naturally, error is less when we consider the central difference case. So in that perspective also, I have used to send. See, this is not the only method. We can try the code with their own coding of having their own substitutions for differential operators. But as far as my knowledge, central difference has less error. So it is feasible to consider the central difference where, not on the boundary. Only when we do the grid generation, you have to take 1 point interior to the left wall and 1 point again interior to the right wall only, not exterior. And how to manage on the boundary and external points means, because I have flux conditions also. When we have flux condition, one grid point lies outside the peripheral bound. So in that case, one should be very wise enough to have at the left wall, we have to consider backward difference, and at the right wall, we have to consider the forward difference. This was really a very challenging scheme for me. And not only the boundary, because when we deal with the one fluid, we have only 4 boundaries. But because it is a 2 fluid model, 8 boundaries. Maybe me and one of my well-wishers in Taiwan, Professor I.C. Liu, we sat for 3-4 months to code this program. At last, we succeeded. We found difficulty with the matching with the boundary conditions. Here, I have given only the final grid generations, how to consider the grids at the boundaries. 0 and 1, that's what. 0 on the boundary, 1 internal, external. Similarly, ny plus 1 and ny. This problem, I have already, not exactly this problem. Initially, in order to code the program, instead of having more terms in the differential equations, what I did is I took both the fluids to be immiscible, but viscous, so that it will be easy for the coding. So that paper is already published in IJHMT last year only. In that paper, I have given detail about the, along with the nodes and all those things, the network and all those things. If you are interested, IJHMT, you just click IJHMT and my name, you can download that paper. So I will not go in detail of that. Who are interested, you can read. So this para justifies about the convergency criteria. So normally convergency criteria, how we do, we tackle in 2 ways, the convergency criteria in numerical processor. One way is that increasing the number of grids, the solution should be stable. The solution should give you similar values. Suppose if I take 50 grids, if I take 100 grids, if I take 150 grids, if I take 200 grids, so the values should not alter. It will alter after 7th, 8th, 9th decimal. But it's enough if I have 8 decimal places. It's more than enough theoretically. So what I have done is to fix how many grids we require, I have done a grid analysis. Grid analysis is simple. Just run the program considering different types of grids. When I observe that considering 100 and 200 grids, I'm getting equal values up to 10 raised minus 8. So I think this is sufficient. This is more than sufficient. So that in that way, we are going to fix the number of grids. Not only that, we also verify with the literature as usual procedure. Whenever we have our own codes to justify our code results, our code is perfect or not, we have to verify with the literature values. So when I consider in the absence of Hartmann number, in the absence of electric load parameter, in the absence of nanoparticles, my code, as I told, was good with the earlier published IJHMT paper. But that is also again not sufficient because it is my paper only. So in that paper, I have compared the results done by Ozotov and also Moshkin and also the classical papers way back on finite difference, that is by D. Velas Davis, and I got good agreement. Therefore, these results can be accepted. Now we go for the results and discussion. So before we fix, of course, because Grashev number, Brinkman number, hardly I have some 4 or 5 parameters, that's all. that is Grashev number, Brinkman number, Hartmann number, electric field load parameter. Phi represents for your what I can say solid volume fraction, that is the concentration of your nanoparticles, and pressure gradient. So while fixing these parameters, I suggest who are hearing, especially for the students, you randomly don't choose. Actually, they are non-dimensional. You are free to choose any value, but cite some papers and check whether they are near to the experimental values. That would be more suitable, though they are general solutions, but still you will have some kind of appreciation if you choose wisely the values for the non-dimensional parameters. So I have referred some of the experimental papers done by Solution, Jonghu, Napuna, and I have taken these values. Okay. What I did is, though my problem is a partial differential equation second order, in order to have beautiful view and to understand the flow structure, I have drawn both three in 3 dimension and 2 dimension, and also in 1 dimension. I will explain how I have considered the 1 dimension. Just for the, in MATLAB we can do it. Visualization can be done in 3D, 2D, and also in 1D. So the first row stands for the 3D view, and the second one stands for the 2D view. So here you know very well that Grashev number, increasing Grashev number, you can see the 3D visualization. When you increase the Grashev number, when 0, that means the flow is only due to forced convection. There is no free convection. So here you have the flow pattern. In the downward direction, you have a curvature, but not in the upward direction. I'll explain the reason. Similarly, when you go for Grashev number 25, that means when you include the buoyancy effects also, the curvature is hiked. That means it is increased at the lower level. And still, if you increase Grashev number, you can clearly visualize that not only in the lower part of the region, also in the upper part, you have a slight increase in the flow structure. This is for the reason that, if you can observe, in my fixation, I have taken electric field load parameter to be -1. So who are working with the electric field load parameter, they know if we consider E equals to 0, if we consider E equals to -1, and if we consider E equals to +1, how the flow structure will be. E equals to 0 means that short circuit. That means there is no supply of electricity. In that case, you will have symmetricity. But when you consider E -1 and E +1, what is the physical meaning of this one? E -1 and E +1 is the current flowing in opposite directions. If you consider E -1 and E +1, the passing of the current is exactly in the opposite direction. So therefore, the flow also will be exactly in the opposite direction. Suppose if E -1, the flow profiles are downwards. If you consider E +1, the flow profiles will be in the upward direction. I think this is sufficient for you to understand why there is an increase in the lower direction only when we consider higher values of Grashev number. So actually, when you consider GR0, E0, then the profiles will be symmetric. But here I have considered E -1, so there is a increase in the lower zone of the duct. This is about the 3D visualization. Now, when we consider the 2D visualization, you can see that the contours in 2D, they are different. You can very well observe that when GR is 0, the contours are to the right of the wall. There are no contours to the left of the wall. That means there is almost no flow. Because ZR0 means what, as I already told, it is for forced convection. So forced convection means BR0. So we have the profiles dense at the right wall. Because of the reason that, in the geometry I explained that, I have considered the temperature TW2 at the right wall, TW1 at the right wall in such a way that TW2 is always greater than TW1. That means heating at the right wall and cooling at the left wall. So when you have heating, naturally velocities will be more at the right wall. So that's why you have dense contours at the right wall. And when you start including the buoyancy forces, that means GR equals to 25, you see that the contours are deteriorated, both at the right and the left. Again, at the left, they are less when compared to the right. Still, if you increase Grashof number, you see in both the parts of the duct, you have streamlines equally distributed. So that is the contribution of Grashof number. And the reason for this type of contours, I think who are expertise in fluid mechanics, they know it. Increasing the buoyancy forces naturally increases the temperature. So if temperature is increased, naturally the velocity is also increased. This is the contribution of buoyancy forces. Now we go for the temperature. You see that we feel 3D pictures, they are almost similar, whatever may be the value of Grashof number. GR0, GR25 and GR50, they look similar. And also 2D contours, they are symmetric, symmetric up from the top to bottom and left and right, but they are non-linear. They are non-linear. You can observe when GR0 and GR25, the contours are more non-linear when compared to GR0. Why this kind of profiles we get? Because temperature is not much affected for the reasons that I have considered flux conditions at the top and bottom. Flux conditions means what? It will not allow the temperature to dissipate. So that's the main reason why we do not find the contribution of temperature for any values if we consider the flux conditions at the top and bottom. If you consider isothermal, the contours will be different. So this is about the how one has to understand the flow problems. This is for the students who understand the flow problems depending on the boundary conditions. And also we see convex here, bulging outside. So temperature field is like bulging outside, which is a convex. Suppose if I take E0, I will come to that graph next. It will be flat and E minus 1 will be concave. And how we are going to draw one-dimensional graphs? I did a little bit of what I can say, I was thinking, because these things do not exactly locate what is the kind of flow pattern, whether the heat is improved or heat is reduced or flow velocity is increased or reduced. I thought better we visualize in one dimension. What I did is, actually we have a 2 dimension, is it not, X and Y? So in order to reduce that into 1 dimension, what I did is, B along Y direction, the range is from 0 to 1. Range is from 0 to 1. And the height is total width is 1. That I have kept as it is, because zone, we have divided the horizontal, so zones I cannot. So what I did, point, say 0.5, at 0.5. So what output which I get from my running the code, I take at y equals to 0.5 only and generate the graphs. So these are the profiles I got it, and this will give some kind of information for us how the flow structure is. As you can see, GR increases, it increases at the right wall, whereas it decreases at the left wall, because as usual, left is cooling, so it decreases, right is heating, so it increases. But you know very well that Grashof number is always helps to promote the temperature. Similarly, the effect of Brinkmann number, that is viscous dissipation effects. So when Brinkmann number is 0, when Brinkmann number is 0.5, and Brinkmann number is 1. Now here also you can observe the nature of profiles, velocity profiles. When BR is 0, in the it is similar to GR0. It is similar to GR0 because it again reduces to Laplace equation only. So the flow structure is same. But when you increase, you can see that there is, though there is no increase in the upper zone, but we see that the flow is pushed, slowly pushing to upper zone. And it is very clear in third figure. You can observe the curvature. One should clearly observe the curvature. Here it is linear, but whereas this curvature is non-linear. So these are the contours. So when there is forced convection, naturally you will have only one cell formation. But when you increase the Brinkmann number, the formation of two cells will start. As you go on increasing the Brinkmann number, the cell formation at the left and right, they go on, because left and right are rigid bodies. So naturally there is an optimum velocity because I am taking laminar. I'm not going for turbulent. So when it is laminar, so it shifts, cells will shift. If you take BR 1.5 or 2, again you get back the similar structure. And these are the temperature contours. So when BR 0, as I told, it is linear. The contours are also straight. You can see that they are very linear because after all, the equation becomes Laplacian. And when you increase BR, see the convexity is more and more as you go on increasing BR 0.5, 1, and also the contours, the shape of the contours are also different. As usual, in order to have the good visualization, we have done for 1D graphs. This very clearly shows that as Brinkmann increases, both velocity and temperature increases. This is once again the physics is, as usual, increasing Brinkmann number is as good as increasing viscous dissipation. So increasing viscous dissipation in turn increases the buoyancy force because theta is there in the velocity equation. Hence velocity also increases. Now go for Hartmann number. So when we apply the magnetic field, you know very well that Lorentz and Lorentzian forces always reduces the velocity. So here also we are obtaining the same results, but since I have taken hitting at the right plate, so we are getting only one cell formation at the right plate. But if you can see in the in the 3D contours also, 3D, as you again the lower region is becoming flat. It is not increasing; it is becoming flat. Flat means decreasing. The contours also, they are you see the inner contour is almost like a circle, but when you increase, it is becoming the width of the circle is increasing, and the shape of the circle is also changing. That means the profiles are flattening. Flattening means the velocity and temperatures, they are here. You can here see. So as you increase, when you take the magnitude, the profiles 4, 8, 12, the velocity is going to decrease. Similarly, the temperature. And going for electric field load parameter, as I have already explained, E equals to 0 constitutes for the short circuit, plus or minus 1 constitutes for the open circuit, and plus or minus 1 implies the flow of current in positive and opposite direction. It is not negative, opposite direction. That's all. So here, when you have -1, you can see that this figure will give you a very clear idea that the velocity profiles are deep in the lower zone, whereas they are deep at the upper region for E equals to plus 1. Okay, so these are the velocity contours, E -1 and E +1. You can see the shape of the contours also. They are exactly reversed. They are exactly reversed. and you have symmetricity in the center of the graph. Now you may question, though we are taking E equals to 0, number of contours are different. This is for the reason that still I have a magnetic effect. If I take magnetic effect also 0, you will get exactly the number of contours in the above, in the zone 1 and zone 2 exactly equal. Similarly, the temperature, here E equals to 0 contributes for the linear, and -1 +1 contributes for the non-linearity. So these are the one-dimensional profiles for the effects of electric field load parameter. I think I have to hurry up. I think I have time now, Professor Nawaz. Okay, going for.
Yes, please continue.
Thank you. Regarding solid volume fraction, this is our actual contribution. When you have solid volume fraction, you know very well that we have to consider solid volume fraction to be less than 1. The percentage should be less than 1. Otherwise, you will have the problem of clogging, sedimentation, and all those things. So while choosing 5, everybody knows this, but still I'm pointing out. So 0 goes for the regular fluid, 0.05 goes for the concentration of the, that means 5% concentration, and 5 equals to 0.1 refers for the 10% concentration of the nanoparticles. Once again, we are having one cell formation only, because I'm fixing the Hartmann number, fixing the electric field load parameter, changing only the solid volume fraction. So naturally, it goes for only one cell formation. Similarly, these are the temperature profiles, and I need to hurry up. So velocity, I will come in the conclusions. The next important part is keeping water as a base fluid. I have used aluminum oxide, copper oxide, and graphite oxide as the nanoparticles. Particularly, I have not used metals, because whenever we are using the comparative analysis, it's better to go for only oxides and only metals. When you go for hybrid nanofluids, then you can take the combinations of both oxides and metals. So here, these are the profiles. As you can see at the outreach that there is no any major changes in the 3D contours or the 2D contours. So even for temperature also. So in order to understand what is its actual contribution, I have drawn one-dimensional. Even one-dimensional graph did not give any clear picture. So I highlighted only the part of it and enlarged the graph. So when we enlarge, that means the effect is not very distinguishable. We can use any oxide. Its effect is not more influential on the flow. However, if we enlarge, we see that aluminum oxide lies in between copper oxide and graphite oxide, even the temperature also. Similarly, we go for keeping copper oxide as the base nanoparticle, changing the base fluid such as water, blood, and engine oil. Here also, I am not happy with the results. I am not finding any what I can say reasonable changes. But once again, enlarged graphs will show that blood naturally have the lowest velocity because it is negative direction. Similarly, temperature has the optimal temperature. I have already explained about the grid independence. So these are the values considering the grid sizes 11, 51, 101, 151, and 201. As you can see, 150, 100, and 200, they are almost same up to 3 to 4 decimal places. And this is the comparative analysis, just to confirm my code is correct or not. So I think you can find all this information in my published paper. But for this paper, table 3 and table 4 are important. That is the velocity and temperature values, because we could not find out the difference. So I put it in numbers. So when you see that at 0.6, when y is 0.6, the velocity for GO is 0.24, 0.24, 0.24. Only it changes at the third decimal place. Even the temperature also changes at the third. So using any oxide does not, no, it changes, but not to the distinguishable, or what I can say, to the noticeable effect. And volumetric flow rate, these are the mathematical, this one, one has to sit and work with this. After running the course, these are the values that I have obtained. I just summarize all these things. Skin friction, average Nusselt number, because this is the major contribution. When we are using, actually the purpose of adding nanoparticles, we have to understand how much is the Nusselt number has increased or decreased using different nanoparticles, using different base fluids, and using different concentrations. So these are the conclusions. So before concluding, I just once again repeat the problem under study. We have considered a rectangular duct, wherein the duct is filled with two immiscible fluids. The upper zone is viscous fluid, purely viscous fluid. The lower zone is filled with viscous fluid only, but electrically conducting and also saturated with nanoparticles. Left wall is cooled and right wall is heated. Upper and bottom walls are insulated. So with this geometry, what are the results we have obtained? The momentum and energy were reinforced in both the zones by promoting GR. Increasing Brinkmann number accelerates the flow only in the upper half region of the region, that too because I have fixed E to be -1. So Hartmann number widens the velocity and thermal contours, and it generates both flow acceleration and strong heating. For the open circuit cases, increase velocity in the lower zone, whereas E equals to 1 advance the velocity in the upper zone. For short circuit, symmetric flow is attained. Temperature is strengthened with a greater electric parameter. Increasing phi, that means when you increase the concentration of the nanoparticles, momentum and thermal fields are naturally reduced. Only in the lower region, that is very important. Upper region, we don't have particles, so you should be particular that the velocity and temperature attain optimum magnitudes with copper oxide in comparison with aluminum oxide and graphite oxide. Among water engineering blood proves to be the better. Why? You know, this is a very important point one should understand. You know very well that when you compare water and blood is a thicker fluid. So naturally velocity should decrease when compared to water and blood. But here we are having blood, the velocity is more because of the reason that we are charging the blood particles. I am applying electric field. So in electromagnetic therapy, if you visit any of the hospitals, why they give electromagnetic therapy? Because when you give electromagnetic therapy, the blood circulation will be fast. Blood circulation will be fast. So when the blood is charged, the velocity increases. That is the main intention. Here also I am getting, when I take blood as a base fluid, velocity increases when compared to water. So flow rate is strongly elevated with higher Grashof number, Brinkmann number and E, whereas it is depleted with M and phi, reduced with Hartmann number and solid volume fraction. And how about the skin friction? Grashof, Hartmann number and Brinkmann increases the skin friction, whereas copper oxide produces highest friction when compared to graphite, and lowest skin friction at both the plates in both the zones. Next, adding different nanoparticles in the base fluid, keeping water as a base fluid, we find that copper oxide nanoparticle do not produce significant changes in the momentum and thermal dissipation. In the absence of electric field and magnetic field, of course, my results are tallying with my own paper, which is published already in IJHMT. This I have submitted my paper. So after it is published, you can have clear, this is only a bird view of my paper. So I thank you for giving me the time and patient hearing. If you have any questions, please proceed.
Okay, my name is Soshio Kirihara. I come from the Osaka University, Japan. And today I would like to talk about directional fabrication of the ceramic components by using ultraviolet laser lithography of additive manufacturing process. So at first, I would like to talk about the stereolithography and the conventional type and the three-dimensional fabrication process. Okay, in our investigation groups, we try to fabricate the various kinds of three-dimensional structures. For example, the periodic structures and the self-similar fractal structures by using ceramics, other metals, and composite materials. Okay, so the plate shape structures and three-dimensional structures were fabricated by using stereolithographies. So this figure shows the principle of the photonic crystals. Today, I would like to talk about the periodic structure fabrications of the photonic crystals. Okay, so here is the dielectric materials. So the periodic structures possible to reflect the electromagnetic wave whose wavelength is similar to the periodicity like this by Bragg diffractions. So in this case, the photonic band gap and prohibited and band gap areas created in the frequency range in the transmissions attenuations. In this case, and the standing wave A and the standing wave B form in the crystal structures, and the standing wave A vibrating in the air region with higher frequency, and the standing wave B vibrating in a material region with a lower frequency. And between higher frequency and the lower frequency, all electromagnetic waves will be reflected by Bragg diffractions. So that in this area, the photonic band gap areas, electromagnetic wave impossible to transmit to the opposite side, and this means a perfect reflections of the electromagnetic wave. Okay, if you create cavity-shaped photonic crystals, you can transmit the electromagnetic wave for one directions, and you can create like the plate-shaped crystals. It realizes the barrier functions of the electromagnetic wave. Of course, the parabolic shape and the photonic crystals realize the direction transmissions of the microwave, millimeter wave, or the more higher frequency electromagnetic wave. Okay, what is the ideal structures of the photonic crystals? The one type is like this, the diamond type, because here the diamond type photonic crystals possible to open the photonic band gap for all crystal direction like this. So this blue band shows the common regions for the all directions photonic band gap. So in this frequency areas, electromagnetic wave impossible to transmit to the any directions of the artificial crystal directions. However, and of course, this photonic crystal is a perfect structures. However, and it is difficult to fabricate like this complicated lattice structures by using a conventional fabrication method. So in our investigation group, we try to fabricate the photonic crystals by using a stereolithography like this. Okay, here this figure shows schematic illustrations of the photonic crystal fabrications. Here is a photosensitive resin. This resin solidifies the UV laser irradiation. So the laser scanning, and we can create like this the line shape and solid materials. And these line structures was created, many lines were created on the like this stage plate. And okay, layer by layer stacking process, we can create the three-dimensional structures. So we can create the plastic three-dimensional structures by using only the laser scanning and the layer by layer stacking. Okay, this figure shows the created and the photonic crystals. In this case, the epoxy mold and inverse the lattice structure, inverse diamond structures was created by stereolithography. And the barium titanate and the paste materials insert into their three-dimensional mold, so we can create a photonic crystal like this. However, it's difficult to inject to the material paste to the three-dimensional mold, so we try to mix the ceramic particles into the photosensitive liquid resins. Okay, and in this case, two-dimensional structures by using laser scanning, and through the layer by layer stacking, we can create a three-dimensional pattern like this. Okay, so we can create by only the laser scanning and the layer by layer stacking, and we can create a complicated shape three-dimensional structures by using a stereolithography process. Okay, this figure shows fabricated diamond photonic crystals. In this case, the titanium dioxide particle was dispersed into the epoxy matrix, and the volume fractions just only the 10%. So the the direct constant is not so high. However, these three-dimensional structures and the periodic structure directions is about 10 millimeters. So the possible to reflect the microwave by using these three-dimensional patterns. Okay, and the microwave property was measured by using like this the metal tubes. Okay, and here is the antennas, and here is antennas, and the microwave transmits the samples, and and the transmission attenuation measured like this. Okay, if the fabricated photonic crystals possible to reflect the electromagnetic wave in the limited frequency range, attenuation will be decreased like this. The U-shape profile will be obtained. Okay, and this figure shows a fabricated titanium dioxide particle dispersed epoxy diamond photonic crystals. You can see the 111 and the 100, 110 crystal plane obtained according to their computer graphic data. Okay, so the microwave transmits to the 111, 100, and 110 directions. Okay, this figure shows a transmission attenuation of the microwave. You can see and all crystal directions, and from 12 gigahertz to the 70 gigahertz, and the band gap form of all crystal directions. For example, the 15 gigahertz microwave impossible to transmit for any directions. This means the perfect reflections. Okay. So the next, and the electromagnetic property of the photonic crystals possible to calculate by using the solving Maxwell equations. In this case, a plane wave propagate into the photonic crystals for all crystal directions. The most important thing, most difficult things, how to enter the three-dimensional structure to the Maxwell equations. However, in this case, a computer graphic data were cut for the 32, 32, 32, and the XYZ data, and the digital data were entered into the Maxwell equation automatically. So, okay, this figure shows obtained electromagnetic band structures. This yellow line shows the Maxwell equations answer. Okay, here there are many Maxwell equation answer, and then of course this lower frequency and also. So there in these areas the Maxwell equation have answers. So the electromagnetic wave possible to transmit to the opposite side. However, you can see that these regions there are no yellow lines. So the electromagnetic wave is impossible to transmit to their opposite side. So this means perfect photonic band gap formation reasons. So these solid circle shows a higher edge and the lower edge of the measured photonic band gap. You can see the calculated result and the measurement result had good agreement. Okay. Anyway, we want to try to control the higher frequency electromagnetic wave, especially called the terahertz wave, the micrometer order wavelength electromagnetic wave. Okay, this far infrared ray regions and possible to detect like this small weapon behind the newspapers, and it possible to detect dangerous rock and by using a transmission viewing system. Anyway, we have to control, we have to fabricate a micrometer order diamond type photonic crystals to control the micrometer order wavelengths and higher frequency terahertz wave. Okay, this figure shows a fabricated and micrometer order photonic crystals by using a conventional stereolithography process. And you can see the micrometer order lattice obtained. However, in this case, we used only the 0.1 millimeter, 100 micrometer spot size laser beam. So it is difficult to create like this micrometer order structures. And the most important thing, these are composite materials. the epoxy matrix absorbs the terahertz wave. So we have to create a more clear micrometer order diamond type three-dimensional structures, and by using a perfect 100% ceramics lattice. Okay, the next process is a nanoparticle pasting process. Okay, we tried to increase the ceramics particle dispersion amount in the photosensitive resins. And in this case, the 40 volume% alumina particles, and in this case, the particle diameter is 170 nanometer, were dispersed into the acrylic, photosensitive acrylic resins, okay, by using a rotation and a revolution mixing machine. In this case, rotation means mixing like this, and the revolution means like this, the mixing. The revolution is the degassing, and the rotation is the mixing of the particles and the solid particles in the liquid phase. Okay, this is a movie that you can see there. Okay, at first the paste material is very hard, higher viscosity. However, if you introduce the stick and turn around the paste, and okay, you can see the paste material shows smoothly fluid flows. Anyway, we can control the viscosity by introductions of the shear stress. So this high viscosity paste was spread on the glass substrate by using a mechanical knife edge, and in this case, a layer thickness and 30 microns. Okay, so the laser beam scanned on the paste surface, so we can create a solid two-dimensional structures. And spread and the laser scanning and the layer by layer stacking process, we can create three-dimensional structures in unsolidified paste materials. After the fabrications, the three-dimensional structures are put out and washing and drying, and we can obtain the composite materials. Okay, so this movie is stereolithography fabrication. Okay, paste materials and spread on the glass substrate. Okay, and this white color is laser scanning. Okay, so the paste materials are spread on the they are over. Okay. Okay, this figure shows a fabricated micrometer order photonic crystals. In this case, the alumina particle are dispersed into the acrylic resin matrix, and the volume fraction is 40%. Okay, okay, you can see the micrometer order. The diamond lattice was obtained by using a laser scanning stereolithography process. So, of course, these are the composite materials. We have to create a full ceramics micrometer order lattice. Okay, by using a conventional dewaxing and sintering process, we can create the full ceramics three-dimensional structures. Okay, and after higher temperature sintering process, we can create the full ceramic diamond lattice. Okay? You can see the diamond planes and 111, the 100, 110. Okay, and you can see the micrometer or the alumina lattice and the translucent lattices. And reached the relative density. In this case, the 99.8% very higher density. Okay, so we can create the full ceramic diamond structures by using a stereolithography and heat treatment process. And the terahertz wave property was measured by using like this optical system. At first, a femtosecond laser beam inserted into the micrometer order antennas and generated the terahertz wave transmit sample and detected the same shape micro antennas, and we can obtain the intensity and the time and the pulse data, so that by using Fourier transformations, and we can obtain the transmission spectrum. Okay, this figure shows obtained transmission attenuations, transmission spectrums. Okay, and you can see there 110, 100, 110 directions, and we can obtain the photonic band gap in the similar frequency range. These blue band shows the common regions of the all crystal directions. For example, the 0.4 terahertz wave impossible to transmit any directions. This means the perfect photonic band gap formation. Okay, the photonic crystals, why we call these structures the photonic crystals, okay? Here is a schematic illustrations of the semiconductors. These materials compose of the periodic structures of atoms. These periodic structures possible to reflect the electronic wave by Bragg diffractions. So in this case, the electron band gap form in the energy band. And if you introduce the donor or the acceptors, the structural defect to the semiconductor, you can create a localized mode in the electronic band gap, and you can control the electronic wave transmissions by introduction of the structural defects. And of course, in the photonic crystals, imitation of the semiconductors and this periodic structure, direct material periodic structures possible to reflect the electromagnetic wave by Bragg diffractions. And the photonic band gap open in the electromagnetic wave transmission spectrums. And if you introduce a structural defect, you can control the electromagnetic wave transmission and create a localized mode in the band gap. Okay, so similar logic, the photonic crystals and the semiconductor natural crystals. Okay, this figure shows introduce a point defect in the perfect photonic band gap. Okay, so of course this hole was fabricated under stereolithographic additive manufacturing process. Okay, this figure shows a calculated result. In this case, the incident wave and the localize and resonate here, and all here is the perfect reflection structures, and making a standing wave increase the powers and transmit to the opposite side. In this case, half wavelength localize here, and in this case, one wavelength localize this directions. And these electromagnetic wave only transmit for opposite side. Okay, this figure shows the the measurement result. The photonic band gap opens by perfect photonic crystal structures, and they introduced the structure defect creates a transmission mode of the transmission peak of the localized modes, okay, in the specific frequencies. Okay. This figure shows the created ceramic crowns. Okay, we can create various kind of three-dimensional structures in the photonic crystals, of course, the photonic crystals and the bioceramic structures, and we can create various kind of materials and three-dimensional structures. However, we have to create the three-dimensional shape by stereolithography, and if you obtain the full ceramic structures, we have to use the heat treatment process. Anyway, we need two processes, shaping and heat treatment. So the next trial, direct ceramics fabrication by using a laser scanning process. Okay, in this case, laser beam, ultraviolet laser beam powers increase to the 1 watt. This is 10 times higher comparing with the conventional stereolithography process. Okay, so increase the power ultraviolet laser beam, realize the waxing and through the resin decompositions and sintering by using electromagnetic wave resonation, localizations, and absorption. Here is the ceramic space materials. After the waxing and sintering process, remaining ceramic particle was sintered and creates the plate-shaped structures on the substrate. Okay, this figure shows a laser drawing process and the bright color obtained the laser spot side. And after laser scanning, we can create like this plate-shaped materials. Okay, here is microstructures. You can see the micrometer or the bulks created in their microstructures about 5 micron to the 8 microns. And of course, at first, the ceramic particle size is under the 1 micrometers, so the micrometer or the bulks were created by laser beam irradiation. The most important is sprayed paste thickness at first 15 micrometers. However, after laser drawing, the layer thickness decreased to the 25 microns. This means the ceramic particles dispersion is 50%. So the waxing and sintering shrinkage occurred to to the only z directions. So it is possible to realize the layer-by-layer stacking process. Anyway, in our investigations, and we used ultraviolet laser beam and 355 nanometer wavelengths. Okay, in this case, a half wavelength easy to propagate between the particles and penetrate into the inside of the paste materials and increase the temperatures. So the resonation and the localization occurred over the inside, so that the resin, the waxing, and the powder sintering were realized the inside of the paste materials. However, if you use like this infrared ray and wavelengths in the very longer, and the laser beam impossible to penetrate into the paste materials, so they're okay by laser beam scattering. Anyway, layer by layer stacking process, we can create micrometer order 3-dimensional structures. In this case, a titan of photonic crystals was created by ultraviolet laser scanning process. And at first, okay, here is a micrometer order structures. However, in this case, the nanoparticle were coagulated into the 3-dimensional structures. So the scanning speed increased to the twice. 2 times, and the scanning speed 100 micrometer per second, so we can obtain the more clear micrometer order structures. However, you can see the black area remained. Of course, this is the remained carbon elements, so the irradiation power was increased to the 600 milliwatt to the 700 milliwatt, so we can obtain the white colors micrometer order titanium dioxide lattice was obtained. In this case, the relative density is 97%. Okay, high density, however, not so. We want to try to do the heat treatment. So, in this case, after heat treatment and the lattice crystal structures was luteal structures or higher dielectric constant. Okay, and by using directional fabrications and ultraviolet laser lithography process, we can create the twin diamond structures. Okay, here is real structures, and this dotted lines twin defect. Okay, here right side and the left side has a mirror symmetric diamond lattice. Here is a plane defect. This area is possible to localize and resonate electromagnetic wave. In this case, the sintering density reached 99.5%. Okay, this is localized simulations, and the wavelengths and the electromagnetic wave localize and resonate here, and reflects my perfect mirror structures and increase the powers and to transmit to the opposite side. Okay, this figure shows the calculated results and measurement results. Here is a band gap, and here is a localized mode formed by introductions of the plane defect of in the twin diamond crystals. Very clear photonic band gap and localized mode was obtained in the measurement results and the calculated results. Okay, in this investigation, we try to fabricate the 3-dimensional structures by using an additive manufacturing process. At first, the 3-dimensional diamond structure was designed, and the 3-dimensional pattern was fabricated by a stereolithographic additive manufacturing. And the electromagnetic wave property was measured by a computer system and obtained the result feedback to the 3-dimensional designing. By using like this investigation circles, we can create the ideal structures, and by using computer-aided design, manufacturing, and evaluation process. Anyway, this is last slide. In our investigation groups, we can fabricate various kinds of 3-dimensional structures. Of course, the ceramic structures and the metal structures and the composite materials. And today, I talk about the periodic structure fabrications and the electromagnetic wave controls by using photonic crystals. Thank you very much.
Screen is visible.
Yes. Please continue.
Good afternoon, one and all, dear professors. Here I am, Done Appa Sahib, and working under the guidance of
Professor J. Pratap Kumar from Department of Mathematics, Gulbarga University, Gulbarga, India. First of all, I am very much thankful to organizing committee for giving me an opportunity to present my talk. The title of my today's presentation is Forced Convection of MHD Boundary Layer Steady Flow Fast Thin Needle with Variable Wall Temperature in Cation Nanofluid. Abstract. This steady flow and heat transfer over a thin needle with variable wall temperature using Cation nanofluid is studied. The conservation equations are then reduced to coupled non-linear ordinary differential equations by means of similarity transformations. The resulting reduced equations are solved numerically by adopting a shooting technique and B4C algorithm available in MATLAB software. The Tiwari and Das model is incorporated to modulate the nanofluid. The metallic nanoparticles such as gold, copper, silver, and diamond are suspended in blood, which is considered as a base fluid. Velocity, temperature, skin friction coefficient, and Nusselt number are computed and presented in graphical and tabular forms. The presence of Cation parameter boosts the velocity but declines the temperature. The Nusselt values are increased using nanofluid in comparison with the regular fluid. Numerical solutions are validated with the literature for limiting conditions and are good agreement. Introduction. In present days, the study of non-Newtonian behavior of a fluid is very important because of its wide range of applications in the field of engineering, technology, and science fields. The Cation fluids are preeminent in the non-Newtonian liquids. This is remarkable that a mathematical model is decreased into a Newtonian of liquid if the yield stress is smaller than the wall stress. Meissner and others et al. Meissner et al. And others have studied this. Most of the liquids involved in realistic models are complex Newtonian. So nanotechnology is a highly interdisciplinary science and deals with areas such as medicine, pharmacology, and drug design, and cancer therapy, etc. The two models that describe the transport behavior in nanofluids are namely reflected by Bayen-Goerno and the other model by Tiwari and Das. The Bayen-Goerno model is a fluid, a non-homogeneous model where the sleep velocity of nanoparticles and base fluid is not equal to 0. Unlike the Bayen-Goerno's model, that the Tiwari and Das model is a homogeneous model in which the thermophysical properties of the base fluid are enhanced by the nanoparticle affecting the correlations of viscosity and thermal conductivity. The effect of a solid nanoparticle volume fraction is found significant in this model. Needle is shaped like a paraboloid of revolution with the axis in the direction of the incident flow. It is considered as thin when its thickness does not surpass the boundary on it, or smaller and parabolic revolution of slandering object is its geometry. Using the model of nanofluid equations proposed by Tiwari and Das, the behavior of the hybrid nanofluid flow and heat transfer over a vertical thin needle with prescribed surface heat flux is studied by Vine et al. Soyer, Krishna et al. And others studied the fluid flow on a horizontal needle. Motivated by the existing study, the present paper aims to investigate the behavior of Cation nanofluid flow and heat transfer past a horizontal thin needle with convective boundary conditions. In this study, nanofluid is considered by suspending gold, silver, copper, and diamond nanoparticles with blood as the base fluid. Geometry of the problem. This is the physical configuration of the problem. The thin needle is placed horizontally. The size is 0 at the leading edge, and it increases towards the other end. X and R are the cylindrical coordinates measured in the axial and radial directions of the needle. UV denoting the velocity components of the velocity along X and R axes respectively. Here UV denotes the velocity of the external flow, and TW variable surface temperature at the geometry. The governing equations in dimensional form are given by the continuity equation. This equation ensures that the fluid must follow the continuum hypothesis. Momentum equation. LHS of the equation denotes the convective term, UE bar upon dx bar denotes the stagnation point, mu nf the viscosity of the nanofluid, and beta used is the Gaussian parameter. Energy equation. LHS, again the convective term. Alpha NF is the thermal diffusivity of the nanofluid. Subject to the boundary conditions, at the leading edge, no slip, that is U bar equals to 0, V bar equals to 0. These are the dimensional equations in dimensional form. TW bar X bar of X bar is the variable surface temperature. UV bar of X bar is the velocity of the external flow. T infinity free stream temperature. The relation between viscosity of nanofluid to the viscosity of base fluid for blood gold nanofluid is defined by Changadar and Day for phi greater than 0.02. Using these dimensionless variables, the above governing system can be transformed into the dimensionless form. As usual, the continuity equation, momentum equation, and the energy equation in reduced form we obtained. I mean, in dimensional form we have with the usual meanings. Using the same transformations, the dimensionless boundary conditions obtained are at the leading edge, again, no slip, U equal to 0, V equal to 0, TW, the velocity in dimensionless form, temperature, variable temperature. U E of X, velocity of the external flow, and T tends to 0 at infinity. Using the similarity transformations, the governing equations were transformed into the nonlinear ordinary differential equations. These strips of functions adapted for this are given here. Setting eta equals to A in equation depicts both shape and size of the needle, having its needle surface is given by R of X equals to 0. Of practical interest, we must have m less than equals to 1. The body represents cylinder when m is equals to 1, and paraboloid when m is equals to 0. And it represents cone when m equals to minus. These similarity transformations reduces the equations into the ordinary differential equations given here. Similarly, the boundary conditions are obtained. It is noteworthy fact that for particle volume fraction phi is equals to 0 and beta, the Casson parameter, tending to infinity, the equation reduces to a Newtonian fluid system. Graphs and discussion. A set of governing ordinary differential equations subject to the given boundary conditions are solved by the method already I have mentioned in the abstract. These are the thermophysical properties of a base fluid and various types of nanoparticles given in the tabular form. Graphical results are drawn by the following figures. This is the boundary layer problem. So the effects are observed at the boundary. If the Casson parameter beta appears in the denominator, thus the velocity, just we see here that in increasing velocity increasing. So figure 2 shows variation in velocity profile with the Casson parameter, and it increases as increases with increase in the Casson parameter. And for the large value of beta Casson parameter, for the large value of beta, it remains constant. See, in figure 3, the temperature decreases with increase in the needle size, parameter A, as the geometry used in this problem is a thin needle. So the slope of the needle surface is decreasing towards the leading edge. So near the boundary, velocity increases. So in figure 4, velocity increases with increase in the volume fraction phi. This is because the shape of thin needle is more parabolic. So the flow of concentrated fluid over the thin needle surface increases the speed. Thus, there is a increase in velocity. Now in figure 5, figure 5 shows that the velocity profile against the various nanoparticles. Various nanoparticles, and it illustrates the velocity profiles for various nanoparticles: gold, silver, copper, and diamond. When the needle size is very less, very small, 0.01, it is clear that the velocity boundary layer thickness is greater for metallic nanoparticles than for non-metallic nanoparticles. It is because of the thermophysical conductivity of gold nanoparticles are higher compared to the other nanoparticles because of its high atomic number. So similarly, the other metallic particles, silver and copper, have higher thermophysical properties as compared to the diamond. So therefore, the gold nanoparticle shows to be has a higher thermal conductivity. It was further found that diamond nanoparticles have the minimum thickness of the velocity boundary layer of all other nanoparticles. Copper and silver nanoparticles have velocity profiles in order of growth, and finally gold nanoparticles show high velocity profile. And for eta, the similarity variable greater than or equal to 4, I mean for a large value of similarity variable, the velocity profile of all types of nanoparticles coincides. They agree and remains constant, steady towards the free stream. Looking into the physical point of view, the increase in volume fraction leads to enhance the viscosity and thermal conductivity of the nanoparticles. The behavior of the thermal boundary layer is in agreement with the decrease of the heat transfer rate from the needle surface of the nanofluid. Figure 6. Increase in the Casson parameter decreases the temperature. So physical insight, escalating or increasing the values of beta Casson parameter gives rise to resistance force, which resists the motion of the liquid, and this is due to increase in the dynamic viscosity, which means reducing the yield stress. This reduces the momentum boundary layer thickness and thereby decreasing the fluid movement and increasing absolute surface velocity gradient. Since the equations are coupled, so the decreasing effect is shown in temperature varying beta. Now next. Figure 7 shows the effect of needle size parameter A on the temperature. As the needle size increases, temperature increases. As the needle size increases, the temperature increases. Figure 8. The variation in the volume fraction phi increases the temperature profile. Figure 9. The temperature, the impact of all the gold nanoparticles, all the nanoparticles on the temperature is shown here. For a small needle size parameter 0.01. Figure 9 shows that the gold nanoparticles have moderately low temperature for small size needle, while the thickness of the temperature boundary is greater for diamond. However, all the 4 temperature profiles are very close to each other. Figure 10. Skin friction with varying the nanoparticle, needle size parameter. At the leading edge, it is clear that for small needle size, the skin friction is very high at the boundary and goes on decreasing with increasing the needle size parameter. And also we see that when A is maximum, needle size parameter is maximum, the decrease in the skin friction parameter is negligible. Figure 11, here in this figure, we have carried the Cassion parameter beta along the volume fraction phi. For high Cassion parameter, large value of Cassion parameter beta, is seen that the skin friction at the boundary is very high, and for large value of beta, the profiles are very close. They are very close to each other, and overall along this beta, skin friction increases. But increasing the volume fraction, we can see that towards the other end, it goes on decreasing. Figure 12, the Nusselt number, effect of the needle size parameter A on the volume fraction phi along this one is sketched in this figure. And here we see that the Nusselt number decreases with increase in the needle size parameter. And in figure 13, as the Cassion parameter increases, it increases the Nusselt number along phi. The table shows comparison of the established solution in present work with the published work. From this, it is observed that our present work is in good agreement with Grossen and Pope et al. Conclusion. In this study, we have analyzed the problem of heat transfer, forced convection, boundary layer flow of various nanoparticles, blood nanofluids over non-isothermal thin needle with convective surface boundary condition. The following results are drawn. The velocity profile increases with increase in Cassion parameter, but decrease with needle size parameter. Further, velocity is found to be an increasing function of a nanoparticle volume fraction phi. The particle velocity near the wall is minimum, that is 0, and approaches a maximum value and remains constant near the free stream. The type of nanofluid plays an important role in heat transfer enhancement. The maximum heat transfer takes place when gold nanoparticles are used. The difference in heat transfer in case of different nanofluids is increased by increasing the needle size parameter and the particle volume fraction. The shear stress from the surface of the needle decreases with the increase in needle size parameter, while increases with Keston parameter. After all, these are the references left. And thank you. Any question, please?
From Ohio University, the final year student of chemical engineering. And it's my immense pleasure to meet you all the different professors and doctors from different fields in this entire colorful and fruitful journey. So here I'm gonna speak and share my screen for the presentation of the importance of green corrosion inhibitors in industries. Okay, can all of you hear me properly and see the screen?
Yes, yes, yes. Please continue.
So generally, when we talk about the first part, which is the green corrosion inhibitors, it has two distinct sections. One is the green, the word green, and the corrosion inhibitors in its including field. So generally, let us talk about a bit of introduction. So that's chemical substances which are extracted from natural sources, which helps the degradation of metals such as iron or its alloys like steel without damaging the ecosystem at a very high scale. They are generally called at the green corrosion inhibitors. And generally in industries, we use corrosion inhibitors which are generally organic compounds and inorganic compounds. But as the technology is rising, as people getting much more advanced methods of experimentations and analysis, they are developing much more advanced mechanisms for plant extracts and biodegradable materials so that the Mother Earth is safe enough. So green corrosion inhibitors has its own classification, but before that, we'll try to analyze the impact of corrosion in a short cast, which is the cost of corrosion. Generally, the corrosion is a very buzzing issue all over the world for industries, for aviation sector, for pharmaceuticals, developments, then the machineries, mechanicals, and mechatronics, robotics. So cost of corrosions can include material and energy, economic impacts can be either direct or indirect, which can be shutdown of the companies, loss of products, loss of efficiency, yield of the products, and the contamination of the useful products and the over-design. It can cause some harmful effects for the life and safety as well. Then the classifications of green corrosion inhibitors can be separated into two of them. One of them can be organic green corrosion inhibitors, and another can be inorganic green corrosion inhibitors. So if I just look into the organic part, we generally see them as ionic liquids, surfactants, biopolymers, plants, drugs, amino acids. Plants can be much more evaluated into much more distinct sectors such as leaf, roots, fruits, flower, oil, whole plant, wooden part, waste, wooden part, and the other waste materials of the plants. Wooden part of the plants can be used as a stem, branch, or the bark. And if we talk about the inorganic green corrosion inhibitors, rare earth elements can be used in different sectors, but mainly we use organic corrosion inhibitors for biodegradable green corrosion inhibitors because they are much more abundant. Okay. Now, generally, what are the properties of corrosion inhibitors that we generally look for as students or as the researchers or as the technicians? Generally, the main thing is greenness, so that non-toxic to the living organizations and environment, then solubility of inhibitor molecule, then they must contain functional group containing heteroatoms like P, phosphorus, nitrogen, oxygen, and sulfur. And inhibitor molecules should possess bulky group extended pi bond and active sites, availability to cover large surface area of metal surface so that they can have enough absorption process. And generally, we know that absorption can be of different types. Absorption isoform, which can be Langmuir, Fromkins, Tamkins, then Alavati. And at last, we can say that it must be cost-effective and biodegradable, renewable, and non-toxic, so that at the end of the day, the green world stays stable. Then generally, when we talk about the types of corrosions, it is generally intrinsic and extrinsic. And so intrinsic includes general corrosion, pitting corrosion, intergranular corrosions, parting corrosion, stress corrosion. Extrinsic can be like stress corrosion, galvanic, erosion, fretting, and the corrosion fracture. Okay, then in general, I will just keep it very simple for all of us. As how does a green corrosion inhibitor work? Generally, it's the overall the mechanism is generally almost the same, but as we go much simpler way, we can say that inhibitors generally decrease or prevent the reaction of the metal with the corrosive media. So they reduce the corrosion rate by the absorption of ions or molecules onto the metal surface. So generally they form a metal inhibitor complex that forms a layer or coating on the top of the metal to reduce its degradations or corrosion. Then increasing or decreasing the anodic and cathodic reactions. These are like charged reactions that take place at the site of the metal. Then decreasing the diffusion rate for the reactants to the surface of the metal, and decreasing the electrical resistance of the metal surface. And we can also say that inhibitors that are often easy to apply and have in situ application advantage. Okay. So benefits of generally when we talk about organic and inorganic corrosion inhibitors, and that we have been using for a few amount of years or over decades, they have a lot of these advantages for the ecosystem that led to researchers much more experiments into finding new and greener alternatives to the existing corrosion inhibitors. In addition to their low cost, ease of access, and regenerative properties, plants have numerous advantages such as environmental friendliness and the ability to produce and dispose the plants in a sustainable way, because we know that day by day, the ease of access of materials less, regenerative properties are challenging to be maintained, and environmental issues are buzzing all over the world, especially countries like India, Bangladesh, and Pakistan. They have to look onto the environmental factors much more compared to other countries mainly, and the ability to produce and dispose of plants in a sustainable way. When we talk about sustainability, we look into the alternative corrosion inhibitors, we look into the environment-friendly materials that are biodegradable, and that you need lower costs to maintain the disposal, to maintain the waste management or waste treatment, so that it becomes much more feasible and it gives as more yield as possible compared to other organic or inorganic corrosion inhibitors. So generally techniques that can be used by the technicians, that can be used by the researchers to demonstrate and analyze the efficiency of a corrosion inhibitor or a green corrosion inhibitor compared to the traditional organic and inorganic corrosion inhibitors can be the weight loss measurements, where they find a percentage of the mass that has been lost due to without the corrosion inhibitors, and with the corrosion inhibitors they can analyze it using a tabular method. Then we can use potential dynamic polarization, then electrochemical impedance spectroscopy. The surface characterization can also be used, such as atomic force microscopy, then electrochemical noise measurements, linear polarization resistance measurements, alternative current impedance measurements, scanning electron microscopy, atomic absorption spectroscopy, centrifugal partition chromatography, galvanostatic polarization. Calorimetric estimations can be done some way in some cases, so that it can give you values and it can give you a clear idea of their characterizations. surface analysis, energy dispersive X-ray spectroscopy. Spectroscopy plays a greater role in understanding the functional groups that can be formed or the complexes that can form onto the surface based on the corrosion inhibitor properties. Like for different reactants, we can be using, as I say, the green corrosion inhibitors can be plants, parts such as leaves, works, stems. So if different sectors might have different properties for different kind of plants. We can do X-ray diffraction analysis, scanning Kelvin probe tests, Cepheid polarization, UV spectroscopy, then FTIR, Fourier transform, infrared spectroscopy, gasmetric measurements, gas chromatography. Gravimetric analysis can be done. Electrochemical measurements are done to find out the properties, and they can use electrochemical frequency modulation. So these are generally the basic things that most of the researchers uses to find the to evaluate, to analyze the properties and the efficiency of the green corrosion inhibitors in different mediums, such as in alkaline medium, it can be used. Simulated seawater, it can be used, then salt water, then acidic medium, and it can be used for copper, alloys, steel, mild steel, low carbon steel, and that gives you a better understanding of whether the corrosion inhibitor is efficient enough to be used with the higher yield against organic and inorganic corrosion inhibitors. Yeah, thank you.
For the opportunity first. Thank you for the opportunity, first of all, given to me. And it was a great experience listening to all the professors speaking at the beginning of the session. It was so interesting. Thank you for that. And today my topic is nanotechnology for microelectronics and optoelectronics. So so about myself, I'll give a short introduction about myself. So my name is Shweta, and I'm currently pursuing my graduation from PSG College of Technology. I'm doing production engineering, and I've done some internship from Internshala and NSIC. That's it. It was a short, brief introduction about myself. So moving on. So nanotechnology is being spoken as a driving force behind new industrial revolution. Both private and public sector are spending constantly increasing. Spending on public research has reached the level of over 3 million worldwide, but the private sector are spending even faster. So we'll see what is nanotechnology. So nanotechnology represents a revolutionary path for technological development that concerns the management of materials at nanometer scale. Nanotechnology facilitates the means any technology on the nanoscale that has numerous applications in the real world. Nanotechnology literally encompasses the fabrication and application of chemical, physical, and biological systems at the scale ranging from individual molecules, atoms, to sub-micron dimensions, and also integration of these. Resulting nanoparticles into larger systems also. It has a potential to change our perspectives and expectation and provide us with the capability to resolve the global issues. The discovery of these materials has allowed the introduction for many years of many areas of technology in nanomedicine, biosensor, bioelectronics. In recent years, nanotechnology has emerged as a multidisciplinary field in which gaining a fundamental understanding of electrical, optical, magnetic, and mechanical properties of nanostructure promises to develop the next generation of fundamental materials with wide-ranging applications. Nanostructures can also provide solution to technological and environmental challenges in the areas of catalysis, medicine, solar energy conversion, and water treatment. Nanotechnology plays a significant role in the advancement of scientific and engineering technology at nanoscale. Over the past few years, nanotechnology has elicited much interest because of its distinct characteristics that influence the physical, electrical, chemical, biological, and optoelectrical properties. So it's hard to imagine how small the nanotechnology is. 1 nanometer is 1 billionth of a meter. It's about like 10 to the power minus 9 of a meter. And an inch consists of 25 crore 4 lakh nanometers. A sheet of paper consists of 1 lakh nanometer thickness. Nanomaterial involves the ability to see and control individual atoms and molecules. Everything in the earth is made up of atoms and molecules. The food that we eat, the cloth that we wear, the buildings, the houses that we live in, and our own body. Something as small as atom is impossible to see through naked eyes. Today, scientists and engineers are finding a wide variety of ways to deliberately make the materials at nanoscale to take advantage of their enhanced properties such as high tensile strength and lighter weight, increased control of light spectrum, greater chemical reactivity than the large-scale counterparts. So now we'll see the history of nanotechnology. So the idea of nanotechnology was born in 1959 when the physicist Richard gave a lecture exposing the idea of building things at atomic and molecular scale. However, the experiment of nanotechnology didn't come on its own until 1981. It was when IBM scientists in Switzerland built the first scanning tunneling microscope. This allowed them to see the single atom by scanning any tiny probe over the surface of a silicon crystal. Further technology have ever since been developed to capture images at atomic scale. These include atomic force microscope, magnetic resonating imaging, and even a kind of modified light microscope. Other significant advances were made in 1985 when the chemists discovered how to create a soccer ball of 60 carbon atom, which is commonly known as Buckminster fullerene. And in 1991, the super strong rolls of carbon atoms called carbon nanotubes were discovered. Both these materials have important application at nano building blocks. Nanotubes have been used into fibers, long threads, and used to create tough plastic, computer chips, etc. Far future might even see the unique properties of nanotubes to build a space elevator. So we'll see types of nanoparticles. While the bulk materials have constant physical property regardless of the size of the nanoparticle it indicates its physical and chemical properties. Thus, the property of the material changes as its size approaches nanoscale proportions and as the percentage of atom at the surface of the material becomes significant. So according to this, we can divide nanoparticle into three: one-dimensional, two-dimensional, and three-dimensional nanoparticles. So speaking about one-dimensional nanoparticle, one-dimensional nanoparticles have thin film or surface coating. They're used in circuitry of computer chips, and they're used for anti-reflective property and hard coatings on eye lenses. They have been used in electronics, chemistry, and engineering. One-dimensional nanoparticles are nanofibers, nanotubular material with fiber. Their length are ranging from 100 nanometer to tens of microns. So this is how it looks, as you can see. Next is 2D nanoparticle, two-dimensional nanoparticle. Two-dimensional nanoparticles have fixed and long nanostructures with thick membranes. They are used to prepare nanopore filters, which are used for small particle separation and filtration. And structural elements such as 0-dimension, 1-dimension, 2-dimension nanoparticles can be distributed in a liquid or solid microscopic matrix or can applied on a substrate. This is how it looks, 2D-dimensional nanoparticle. And when we speak about three-dimensional nanoparticle, three-dimensional nanoparticles are fixed and small nanostructures where thin films are deposited under conditions that generate atomic scale porosity, colloids, and free nanoparticle with various morphologies. Unlike one-dimensional nanoparticle, two-dimensional and three-dimensional nanoparticles possess health risk due to their free long aspect ratio nanowires and nanoparticle respectively. Three-dimensional nanoparticle includes powders, fabulous, multi-layer, and polycrystalline materials in which the 0-dimension, 1-dimension, 2-dimensional structures are in close contact with each other to form interfaces. The important type of Three-dimensional nanoparticle material is compact or consolidated into polycrystalline with nano-sized grains. So we'll see the properties of nanoparticles. Properties of nanoparticles are flexibility, lightweight, higher density of integration, faster response, lower cost, less consumption. So these are the 6 major properties of nanoparticles, due to which it has a wide range of application and variety of fields. So we'll see a video. Yeah, so that's how nanotechnology works. You can see the power of nanotechnology, which could make an efficient change in future also. So we'll see the nanotechnology in microelectronics and optoelectronics. First, we'll see what is microelectronics. Microelectronics is a subdivision of field of electronics that deals with the small and microscopic elements to manufacture electronic components. So the components of microelectronics. Microelectronic devices are made using semiconductor devices like silicon or germanium. The components that make up microelectronic devices comprises capacitors, transistors, resistors, diodes, inductors, conductors, and insulators. Transistors and other microelectronic components are made by using microelectronic technology on a surface of silicon. The silicon or the integrated circuit is a complete circuit that measures just some millimeter square. So what is optoelectronics? Optoelectronics is a study and the application of light emitting or light detecting devices. It is widely considered as a sub-discipline of photonics. This is how it looks. And components of photoelectronics. Photoelectronic devices refers to the components used to detect or emit electromagnetic induction, typically in the visible nor near the infrared regions of electromagnetic spectrum. Each of these function exploits the photoelectronic effect of material, which was known as light matter interaction. This premise was established by Albert Einstein, who postulated that light was quantized and form of photon instead of continuous wave. Underlying the mechanism of all optoelectronic devices are based on photovoltaic effect, which refers to the emission of electrons from material by photons. So we'll see the progress and development of microelectronics in nanoscale. There are presently a lot of efforts has to be taken to benefit the nanotechnology, but both nanotechnology and microelectronics have opened up areas for new research and development, something that would have been unthinkable to achieve many years ago. We are in an era of speed, light, development, and research. Yesterday's breakthrough might become absolute tomorrow. However, a lot still needs to be done to transform the outcome of numerous researchers on microelectronics and nanotechnology into meaningful job opportunities, economic growth, and better quality of life. Having analyzed the economic importance of microelectronics and nanotechnology, there seems to be a well-defined path for future growth on larger scale. There is a larger pie to be understood in future, but it is all sincerely shouldn't be for the financial gain only. The application of advanced nanomaterials on microelectronic devices have been highly developing due to the flexibility and lightweight for the daily use, which has a potential to be deployable. Nanomaterials, which provide one of the greatest potential for removing performance and extending their capabilities of producing a number of industry sectors, are the new class materials having dimension in a range of 1 to 100 nanometer range. The most successful example seen in microelectronics is invention of transistors. Excuse me. Microelectronics technology and industry has advanced in a considerable extent over the last 2 decades. Now we'll see the application of microelectronics. Microelectronics is an important interdisciplinary technology. Without microelectronics, there would be no computers, no cars, no industrial production, or no identity cards that we know today. Microelectronics is one of the most important key technology for innovations, either integrated into new products or serving as a technology basis for services. Microelectronics offers solution to important societal and economic challenges. Microelectronic systems are a fundamental prerequisites for competitiveness. Microelectronics has a key driver for specific scientific and technological processes that has made major contribution to societal and economic growth of mankind since mid-20th century. Microelectronics has played an important role in the sectors such as mobile phones and telecommunication, multimedia application and digital media systems, computing and networking, clean production process for factories, safer vehicles, and better performing medical systems. So we'll see the major 3 fields where microelectronics application. The first one is 3D integration. Integrated circuits are usually have only one layer of electronic devices, which limits the performance and functionality. A 3D integrated circuit that incorporates multiple device layer enables the wealth of application. This technology allows several traditional devices layered to be placed on stacks and interconnected electronically. As emerging technology, the trend is its support for more functional and powerful devices that are smaller and of low cost. Stacking of many layers of a device can improve the performance of the circuit and lower the power consumption. So 3D integration principle provides manufacturer the flexibility to combine other heterogeneous devices into single circuit. So the next application is haptic touch screen. So we all know the importance of touch. The feel of touch is 5 times faster than vision, and researchers the touch is the first of 5 sense we can develop as infant. Researchers agree that it is most immediate and intimate one, and that interaction and the physical connections are essential for our emotions and social health, which is more than the visual sense. Haptic technology offers a user truly immersive experience when using touchscreen interfaces. Direct information share can be done from the display to the finger point. The touch technology has brought new approach to interact with our devices. This allows the human-computer relationship with various physical contact with the device, such as gesture and the touch. The major applications of this technology are consumer electronics, medical, automotive, and in the industry and in human automation. So when we see the last application is clean electronics. Iceberg bigger than New York City breaking off in Antarctica, raging forest fire in various parts of the world, disappearing of rainforest is just some of the problems we are facing due to climate changes. If we don't make any change, our nature resources will deplete as a trash, continue to pile up and fill our lands and oceans. Green technology is one of the tools that can combat this global crisis. Green electronics utilizes the material in the manufacturing that are environmentally and eco-friendly, biodegradable, recyclable, and sustainable, that do not add to or global problem of e-waste. This is pushed by the government for green manufacturing, which is a driver for the innovation of microelectronics, the product design. Production are altered towards the energy efficiency, green and clean solution. This technology incorporates the power saving capability, eco-friendliness such as reduced carbon emission during microelectronics. So next we'll see a video. So this is how the future will look if the nanotechnology enhances and improves step by step. So now we'll still look at the advancement and the outlook for future. Microelectronics, photonics, and optoelectronic devices based on semiconductors constitute the core technologies of tablet, PCs, smartphone, GPS navigation systems, high definition flat panel display, digital camera, information processing technologies, sensors for automobile. In all microelectronic technology based semiconductor devices, an integrated system has changed daily life. This devices extend the influence to several sectors, including communication, space, medicine, defense, etc. According to the performance, functionality, and the cost of semiconductor devices, determine the added value for many of the previously mentioned commercial products. Demand for microelectronics is going to enhance the speed and storage capacity of next generation devices. The development of integrated circuits and semiconductors have revolutionized the society from communication to information storage to transport and media. The creation and implementation of wide variety of digital devices to the daily lives would not be possible without these technology. So next we'll be seeing the progress and development of optoelectronics in nanoscale. The use of nanostructured materials for optoelectronic devices has recently attracted considerable attention due to unique geometry that they possess. The scientific context, optoelectronic deals with the study and application of electronic devices that interact with light which might be detection of light, its creation and exploitation of several purposes. Optoelectronics is a communication between optics and electronics, which includes study, design, manufacture of hardware devices that converts electrical energy into light energy through semiconductors. The device is made from the solid crystal materials, which is lighter than the metals, heavier than the insulators. Optoelectronics devices is basically an electronic device involving light. This device can be found in many optoelectronic applications like military services, telecommunication, automatic access control system, and medical equipments, etc. Next, we'll see about the application of optoelectronic. It's resonating turning diodes. Resonant turning diodes are nanotech electronic structures that can be easily integrated with conventional electronic and photonic devices. They have two distinct features that are potential for extremely high frequency operation up to terahertz and their negative differential conductance. The former rise from a very small of resonant turning structure along with the direction of carrier transport. The second corresponds to the electric gain, which makes possible to operate these as amplifier and oscillator, significantly reducing the number of elements required for the given function. The functional subay of these devices are based on devices and circuits spanned from the signal generator, detector, and mixture, multi-valid logic switch, low power amplifier, local oscillator, frequency locking circuits, etc. Aiming at this application is high speed for optoelectronic converters such as light emitter, light modulator, and light detector. So challenges of microelectronics. As the size shrinks, the circuit board intently becomes denser. The designers need to pack more input or output into a smaller space and make this array of pad as close together as possible. This problem here is that as the pinch becomes tighter and tighter, so too it does the trace in space that creates signal reliability challenges on the typical circuit board. The signal on the trace loses their energy as the trace becomes smaller. Due to this simple fact that incredibly difficult to ensure the uniform trace of signals when they are relying on subtractive circuit board printing methods on the micro level. This could potentially create a significant problem for microelectronics themselves. Perhaps most notably, the weaker signal strength would lead to reduce the battery life. This is an increasingly important issue for electronics in a wide range of space, including all of those highlighted above. In the case, consumer electronics are in obvious demand for cell phones and other devices that can last as possible without need to recharge. For other microelectronic concerns such as IoT, sensor implants, recharging may be unfeasible or impossible as the devices themselves are simply unreachable. So any micro design that does not fully account to the challenges of the microelectronics passed by increasing the board density will run the risk of failing to meet its full potential. So now we were discussing the challenges faced by microelectronics. So how can we overcome that? So most notably, the tighter trace or space on the circuit board causes the signal loss, which leads to a wide range of problems. This includes diminished battery life and less efficient energy storage, both of which are severely undermines the value of new microelectronic design. The ideal solution for this problem is to utilize smaller PCBs that can accommodate these shrinkage sizes without subsequent drop in the quality. Naturally, that's easier than to be said than done. Typically, the PCB industry movement towards micro has been driven forward by the demand from the device designers and the manufacturers, but there are, or at least have been, limits to minimize the size of trays and space as well as the circuit board itself. Recently, however, the advances in micro PCB technology have made possible to accommodate this shift. The key development is additive processing. We'll see about additing versus subtractive micro PCBs. Recently, until recently, 3 miles was the minimum width of PCB traces and spaces. The problem wasn't the PCB manufacturers were unable to produce a line below this number. It couldn't be smaller without sacrificing the consistency and accuracy. It was the inherent problem with subtractive approach of micro circuitry printing process. This traditional approach is not precise at small size, and as such, it will always be a degree of uncertainty in terms of the line thickness. As electronics and circuit get smaller, the lack of precision becomes more problematic and less acceptable. With additive base printed circuit board process, this is no longer the case. Rather than removing the copper, additing approach involves additing copper to the PCB. This technique is far more accurate, allowing the manufacturer to deliver small tracing places and greater density per inch without encountering signal loss problem highlighted above. So yeah, that is how we overcome the problem. And limitations of optoelectronics. Optoelectronic devices are temperature sensitive. The coupling requires precise alignment of optoelectronic components, which is complex. Optoelectronics or photonic packing requires extremely accurate placement of components to ensure the appropriate suitable alignment and coupling of light into and out of the devices. In many cases, a generation of or detection of light results in significant heat being generated, which if not suitably dissipated through the appropriate joining technology and material selection, can adversely affect the device operation. Additionally, assembly processes can be complicated by requirements that fluxes the organic materials cannot be used, as they degrade the performance of optical devices. Integration of optoelectronic elements onto substrate is difficult. Hybrid integration involves combining optoelectronic devices and integrated circuits in a same package or substrate. This can be done by traditional hybrid technique for simply combining the technology devices on ceramic substrates, but the device density of resulting optoelectronic integrated circuit is very low, and many of the advantages is lost. So subsequently, alternate hybrid techniques have to be proposed to increase the device intensity while maintaining the manufacturability. Currently, the most successful such as techniques involve flip-flop, solid ball, or pump integration of the discrete optoelectronic devices on multiple chip models or directly on the silicon IC chips. But even these techniques consume an inordinate amount of area, and even higher densities are needed. Future scope of optoelectronic devices. Optoelectronic is a vital foundation technology that is enabling seamless functioning of information industry. Academically, optoelectronics encompasses the study of electronic devices for transmission, emission, modulation of light signal. However, its scope has widened today, and it includes electro-optics and photo-optics as well. Commercially significant technologies for material science, communication, computing, and materials are leaping onwards due to the advancement of optoelectronics. Optoelectronics are providing a bigger venue for R&D today. Its effect has been seen in the areas of cost reduction, performance improvement, and large volume manufacturing. Industries and academic committees are predicting a bright future for research in optoelectronic technology. And yeah. So nanotechnology is a blessing or a curse for developing nations. The science of nanotech is cutting edge, but simple enough to be affordable globally. The development prospect is huge, so it's no surprise that many developing countries have already embarked on commercializing the technology. But the blossoming of relatively new technology raises the concern about long-term safety of human health and environment, with many scientists calling for the better and more internationally coordinated regulations and oversight of profilating uses of nanoparticles. Developing nations have left out of conversation about nanotech regulations, and there are still to be better regulations of technology at national and global level to ensure the technology meets the need of the poor with minimum risk of people. And yeah, so challenges of nanotechnology, even after possessing so much of quality, it's not being so prominent in today's world. Nanotechnology has a lot of challenges. The main is environmental pollution. Some of the most extravagant negative future scenarios have been debunked by the experts in nanotechnology. For example, the so-called gray ghost scenario, where self-replicating nanobots consume everything around them to make the copy themselves, once widely discussed but no longer considered as a credible threat. It's possible, however, that it will be some negative effects on environmental, as the potential new toxins and pollutants can be created by nanotechnology. Next is economic upheaval. It's likely that nanotechnology, like other technology before, it will cause a major change in the economic areas. Although the products made possible by nanotechnology was initially expensive, it will be luxury. But once the availability increases, more and more market will feel the impact. Some technology and material become obsolete, leading to the companies specializing in those area will be out of business. Changes in the manufacturing process brought about technology may result in job losses also. So next is privacy and security. Nanotechnology raises the possibility of microscopic recording devices which would virtually be undetectable. More seriously, it is possible that nanotechnology could be weaponized. Atomic weapons could be easily created, and novel weapons might be developed also. One possibility is called smart bullet. It's a computerized bullet which is controlled and aimed very accurately. These developments may prove a boon to military. If it's in the wrong hands, its consequences would be dire. And the last is physiotoxicity. The plants are the essential base component for all ecosystem and plays a crucial role in the fate and the transport of engineering nanoparticle in the environment. Though plant uptake and bioaccumulation, it is also important to mention that bioaccumulation, biomagnification, biotransformation of engineering nanoparticle and food crops are still not well understood. Few nanoparticle and the plant species have studied with respect to the accumulation and substitute availability of nanoparticle in food crops. So the last topic is green nanotechnology. There is a general perception that nanotechnology will have a significant impact on developing green and clean technology with considerable environmental benefits. The best example to use nanotechnology in the areas ranging from water treatment to energy breakthrough and hydrogen application. As a matter of fact, that renewable energy application probably are the areas where nanotechnology will make the first class commercial outbreaks. Green nanotechnology can proactively influence the design of nanomaterial and products by eliminating or minimizing the pollution from the production of nanomaterial. Talking about the life cycle approach of nano products to estimate and mitigate the environmental impact might occur in the product chain, designing toxicity out of nanomaterial and using nanomaterial to treat the existing environmental problems. Green nanotechnology does not rise, but it builds the principle of green chemistry. Green engineering focuses through the new lens on unique and often contagious effects that occurs in nanoscale materials. So yeah, thank you so much.
Myself, Prashant Sutkar, research scholar working in Department of Mathematics, Gulbarga University, Gulbarga, Karnataka. Firstly, I thanks to organizer for giving me opportunity to present my work. My title of the presentation is Flow Characteristics of Micropolar Nanofluid Sandwiched Between Viscous Permeable Fluids. Abstract. The flow and heat transfer of micropolar nanofluid sandwiched between porous medium in a horizontal channel is analyzed. The model is developed to study the behavior of micropolar nanofluid, taking into account the solid volume fraction and porous parameter. Using Darcy's law for porous medium and Tiwari-Das model for nanofluid, governing equations are obtained. The governing equations are solved using analytical method. Water and glycerin is taken as base fluid, and copper as nanoparticles for the analysis. It is found that Grashof number, Prandtl number, Eckert number promotes the flow, Reynolds number, and material parameter suppress the flow. Moreover, for different physical parameters, the rate of heat transfer, mass flow rate, and skin friction is illustrated in table form. The solvent viscosity for air, water, and glycerin, the cell rotation on the flow is presented in tabular form for 20% and 40% concentration. Introduction. The theory of micropolar fluids has received much attention in the last several years because the traditional Newtonian fluids cannot precisely describe the characteristics of fluid flow for a fluid with suspended particles. Physically, micropolar fluids may be described as the non-Newtonian fluids consisting of short, rigid, cylindrical elements, polymer fluids, fluid suspensions, animal blood, etc. The theory of micropolar fluids was first proposed by Engine. The boundary and interface conditions are given by Ehrimann et al. Porous matrix is the material which has pores or voids in it. Beavers and Joseph investigated the behavior of fluid flowing in channels partly filled with porous material. Immiscible fluids are those which won't mix to give single phase. Oil and water are examples of immiscible liquids. Elmabaum et al. Studied electromagnetic flow for two-layer immiscible fluids. Zhang et al. Worked on relative permeability of three immiscible fluids in random porous media, determined by lattice-Boltzmann method. The application extend to include many fields like petroleum engineering, where it is important to investigate the natural gas flow and oil through the reservoirs, agricultural engineering, chemical engineering, etc. Umavati madam and her research group also worked on flow and heat transfer of Newtonian, non-Newtonian fluid sandwiched between viscous fluid layer. Keeping in view the physiological and industrial importance, the present problem is posed with peripheral layer of viscous permeable fluid and the core of micropolar nanofluid in a horizontal channel. Physical configuration. Physical configuration considered in this study is shown in figure. We consider a steady laminar flow of two immiscible fluids filled in vertical channel. The x-axis is taken parallel to the channel, while the y-axis is taken perpendicular to it. The width of the channel is from -h to twice h. The viscous permeable fluid is filled in -h to 0 and 0 to twice h region, having density ρf, the viscosity μf, thermal conductivity kf, and thermal expansion coefficient beta f. The core region is occupied by micropolar nanofluid having density ρnf, viscosity μnf, and thermal conductivity knf. The boundary walls of the channel are held at different constant temperatures. Tw1 is the temperature at right wall and Tw2 is at left wall, with heating at the right wall and cooling at the left wall. mathematical formulation, the flow is unidirectional, so the components of velocity v and w are 0. The equations for steady one-dimensional velocity and temperature for permeable fluids are given by. It contains the equations. In this equation, first term is viscous force, mu of d2u1 by dy square, rho f g beta f t1 minus tw2 is gravitational force, mu f by k into u1 is porosity effect, and dou p over dou x is pressure gradient. Second equation is energy equation, in which first term is kf d square t1 over dy square is the thermal conductivity. Second term is mu f du1 over dy square is viscous dissipation, and third term is mu f k into u1 square is equals to 0 is Darcy dissipation. The equations based on experimental results of Bulgario and Sevilla and a two fluid model with 4 micropolar fluid are given by, in which first one is the for velocity, u2 is the velocity, n is the microtation velocity, delta p over delta x is pressure gradient, and knf d square t2 and dy square is the thermal conductivity. Region third, the equations for steady one-dimensional velocity and temperature for permeable fluid in region third are given by Vf d square u3 over dy square is the viscous term. Second term, rho f g beta f into t3 minus tw2 is gravitational force. Mu f by k into u3 is porosity effect, and dou p over dou x is pressure gradient. In the energy equation, first term is kf d square t3 over dy square is conductivity, thermal conductivity. Second term is viscous dissipation, and third one is mu f divided by k into u3 square is Darcy dissipation. The approximate boundary and interface conditions on the velocity, cell rotation velocity at the interfaces as proposed by Ehrenmann et al. Are given by. First two conditions are no slip conditions, that is velocity at these walls is 0. Second two conditions are the continuity of velocity at the interfaces, and next two conditions are the continuity of shear stress, and last two conditions are the micro-rotation velocity, that is micro-rotation velocity at the core region is 0. The other 6 conditions on the temperature are given by the temperature at the wall at 2H is Tw1, and temperature at the wall minus H is Tw2, that is fixed temperature. The second condition and third condition, T1 of H is equals to T2 of H, and T2 of 0 is equals to T3 of 0 are continuity of temperature. And the last two conditions are the heat flux at the two interfaces of the region. Basic equations in non-dimensional form. The governing equations are made dimensionless using the dimensionless parameters given as, that is given by y star is equals to y by h, ui star is equals to ui by ui divided by u bar, where I is varying from 1 to 3. Similarly for temperature theta I, micro-rotation velocity n star, material parameter k. Okay. So using this basic equations in non-dimensional form, so we have the coupled non-linear second order differential equation. given as in region 1, there are parameters, Grisham number, Reynolds number, and sigma is the porosity parameter. EC is Eckert number, and PR is the Prandtl number. So we have the equation 4A, 4B. Similarly, for region 2nd, we have equation 5A, 5B, 5C. Similarly, for region 3rd, we have momentum equation and energy equation given by 6A and 6B, which depends on GRR, Grisham number, Reynolds number, Eckert number, Prandtl number, porosity parameter. Solution method. The equations are coupled non-linear ordinary differential equations, and hence exact solutions are not possible. However, for smaller values of epsilon, that epsilon is defined by product of Eckert number and Prandtl number. Approximate solutions can be extracted through regular perturbation method. The Eckert number is usually very small, and the Prandtl number takes maximum value of 2-digit in values. The product of Prandtl number and Eckert number is small, and hence regular perturbation method can be strongly justified here. Here, the velocity in region 1, region 2, region 3 is given by UI. I is from 1 to 3 for region 1, region 2, region 3. So UI of Y is equals to UI of 0 at Y plus epsilon UI1 of Y plus epsilon square UI2 of Y. So this is a series solution for the velocity. Similarly, for temperature, it is given by theta I of Y is equals to theta I0 of Y plus epsilon theta I1 of Y plus epsilon square theta I2 of Y. Similarly, for micro rotation velocity, it is in the core region is given by N2 of Y for I is varying from 1, 2, and 6 for the 3 regions. The solutions for non-dimensional velocities U, the micro-rotation velocity N, and temperature theta are obtained as the zeroth order solutions are given by theta 10, theta 20, theta 30. Similarly, for velocity U10, U20, UN20, and U30 for region 1, region 2, and region 3. Similarly, in the same way, the first order solutions are obtained by using the perturbation method. For temperature, it is given theta 11, theta 21, theta 31. For velocity, U11, U21, N21, U31. So with various constants from C1, C2 to C70, and for D also. Special case for Newtonian fluid, solution for the velocities U and temperature are given by. We have micropolar nanofluid in the core region, but instead of that, we can take Newtonian fluid, and for the Newtonian fluid, the value of kappa is 0. So the first order solutions, zeroth order solutions are given by theta 10, theta 20, theta 30 for the temperature, and for velocity U10, U20, U30. So there are no micro rotations, so micro rotation velocity is absent, so the value of N is 0. The special case 1, in which the first order solutions are given by theta 11, theta 21, theta 31 for temperature, and U11, U21, U31 for velocity. Case 2, for Newtonian fluid, and in the absence of viscous dissipation, the solutions are given by. Here, in case 2nd, there is only Newtonian fluid and viscous dissipation is absent. So the solutions are for the region 1, region 2, and for the region 3 are given by theta 1, theta 2, theta 2 for the temperatures, and U1, U2, U3 are for the velocities in region 1, region 2, and region 3 with some constants. Now, Now the effect of velocity and temperature profile for different values of Grashof number GR. The Grashof number is a dimensional quantity used in analyzing the velocity. Grashof number depends on buoyancy force and viscous force. The deriving force is a buoyancy force caused by a temperature gradient, which says that the fluid would be at rest in the absence of temperature variations. Here, temperature variations occurs, which results in increase of buoyancy force, and therefore velocity and temperature increases in the three regions for Newtonian and non-Newtonian fluid. The magnitude of velocity and temperature profile for non-Newtonian fluids is slightly greater than Newtonian fluid, which is shown in the figures. Velocity and temperature profile for different values of Prandtl number. In the figure, the two figures are there. First figure is for velocity profile for different values of Prandtl number, and second figure is for temperature profile for different values of the Prandtl number. Physically, Prandtl number represents the ratio of viscous force to thermal force and is a measure of the relative importance of viscosity and heat conduction in flow field. The Prandtl number depends only on the physical properties of the fluid. Prandtl number increases when viscosity suppresses the conduction. Here, in the first figure, we observe that velocity, and in second figure, temperature profile shows increase in profile for increasing value of Prandtl number. Moreover, magnitude of velocity and temperature profile for non-Newtonian fluid is higher than Newtonian fluid in all the three regions. Velocity and temperature profile for different values of Eckert number. First figure shows the velocity profile for the different Eckert number, and second figure shows the temperature profile for different values of the Eckert number. The Eckert number provides a measure of the kinetic energy of the flow relative to thermal energy. Eckert number increases when kinetic energy is more or the velocity is more than the thermal energy or the thermal or the heat dissipation. When the magnitude of kinetic energy is greater than heat dissipation. When average velocity have greater value than heat dissipation, which results in increase in velocity and temperature profiles for both Newtonian and non-Newtonian fluids, which is shown in figure. The velocity and temperature profile for different values of material parameter. The first geometry shows that the velocity profile for the values of material parameter, and second geometry shows that the velocity profile for temperature profile for the material parameter K. Material parameter is the ratio of vortex viscosity and viscosity of micropolar nanofluid. Material parameter is directly proportional to vortex viscosity and inversely proportional to viscosity of micropolar nanofluid. As vortex viscosity increases more than viscosity of micropolar nanofluid, velocity decreases in all the three regions that we can see in the geometry, except for the value of 0, except for the value of decreases for decrease in vortex viscosity in all the three regions. Velocity profile for different values of porous parameter. Porosity depends on width of the region and permeability of porous medium. The width of the channel is unit, so the porosity is inversely proportional to permeability of porous medium. As permeability of porous medium decreases, porosity increases, so there is disturbance in the flow speed, which results in decrease of velocity for both Newtonian and non-Newtonian fluid in all the three regions. Temperature profile for different values of porous parameter. That is, the graph is drawn for the value of Newtonian fluid and non-Newtonian fluid. That is for sigma is equals to value for 2 unit, 4 unit, 6 unit, and 8 unit. In case of non-Newtonian fluids, the core region is occupied by micropolar nanofluid, microrotation component, and nanoparticle present in the core region enhance heat transfer in all the three regions, while in Newtonian fluid, temperature decreases due to force in regions 1 and 3. Velocity profile for different values of solid volume fraction. In general, velocity of any flowing fluid depends on the viscosity. Here, nanoparticles are added in the flow, which behaves as constant. So, figure shows that there is decrease in velocity as we increase value of the solid volume fraction. Similarly, the temperature profile for different values of solid volume fraction. As solid volume fraction increases, both the velocity and temperature decreases. One can justify this result by saying that as the nanoparticles are added to the pure fluid, the density of fluid increases and the fluid becomes denser, which results in decrease of momentum of the fluid in the channel. So this slide contains microrotation velocity profile for different values of material parameter K and solid volume fraction, which is shown in the figure. Microrotation velocity profile for different values of porous parameter is shown in the figure. Variation of effective viscosity on velocity profile and microrotation velocity profile. Velocity and microrotation velocity profile is illustrated for effective viscosity as in the figures. The shear viscosity μnf of micropolar fluid on the velocity and microrotation velocity for 20% and 40% concentration has been computed and is shown graphically. So these are the table which have the variation of cell rotational viscosity for different solvent viscosity on velocity in region second. So this is taken for air, water, and glycerin for the values of μr, that is 0.78 and 0.98. Table second, the variation of cell rotation viscosity for different solid viscosity on microrotation velocity in region second is given in the table 2, and variation for temperature is given in the table 3. Last table, the rate of heat transfer and skin friction at the top and bottom plate and the mass flow rate for different values of Eckert number, Prandtl number, Grashof number, Reynolds number, porosity parameter, and solid volume fraction is given by for different values, that is for 1, 2, 3, and 4. So we have all the values that are illustrated in table form. So comparison of this results. The results obtained in this article matches with the result as in the research paper. Flow and heat transfer of micropolar fluid sandwiched between viscous fluid layers by Jc Umavati, J. Pratap Kumar, and A.J. Chamka. This matches, my results matches with this paper if the value of solid volume fraction is 0 and porous parameter is 0. That means porosity is absent. If porosity is absent, that is the value of 0, and solid volume fraction is absent. So the result matches with this paper. Conclusion: this work illustrates fluid flow and heat transfer in horizontal channel consisting of micropolar nanofluid as core region surrounded by porous matrix. The solutions are represented graphically for various governing parameters like Grashof number, Prandtl number, Reynolds number, solid volume fraction, porous parameter, and material parameter for velocity, micro-rotation velocity, and temperature profile. It is observed that effect of Grisham number, Prandtl number, Eckert number promotes the flow in all the three regions. Solid volume fraction, material parameter, and porous parameter affects the flow. The solvent viscosity for air, water, and glycerin, the cell rotation on the flow is presented in tabular form for 20% and 40% concentration. So these are some references I have referred for the study of this article. Thank you, sir, for giving me an opportunity to present over here.
Yes, thank you, Mr. Prashant, for the valuable presentation. Any questions for Mr. Prashant?
Excuse me, may I have
Yes.
some question, okay?
Yes, please. Yes, please.
Thank you so much for your fruitful talk, okay? Could you please show me the presentation sheet page 14 is assigned for it. Page 14.
Yes, sir.
Yes, this one. Okay, thank you so much. Perhaps for the purpose of obtaining this solution, you used the perturbation method. I think so.
Yes, sir. Yes, sir.
And yes, but perhaps I requires you to solve the non-linear system of equations. Perhaps I think so.
Yes, sir. Yes, sir.
Yes.
Yes, sir. Yes, sir.
So this solution seems to be so beautiful and yes, concise and clear. I think it seems to be so complicated solution may be obtained or not. How do you think? Non-linear systems of equations cannot be written so clearly.
Yes, sir. Yes, sir.
But this solution seems to be so clear.
Okay, sir.
Could you please tell me the some innovative ways developed by you, if possible?
Okay, so we have tried for exact solution, but the equations are
Yes, this one. Yes,
coupled.
okay. For example,
This equation like this. We can see the
two
equations are
2 pages before. Okay.
yes.
From
So these equations are coupled. So we can't find exact solution.
yes.
We have used perturbation method, sir. And to use perturbation method, we have formulated our problem like this: ui of y is equals to ui0 of y plus epsilon ui1 of y plus epsilon go. So
but
this
the
is the
square
series
of
solution
epsilon.
for yes, sir,
Epsilon to the
yes.
second term is included in this system. So
yes, sir.
it seems to be so difficult
so
for
higher
us.
derivatives. Yes, sir. We are tried for 0th order and 1st order, and we are getting the solution. As we in physics, the third derivative or fourth derivative or higher derivatives, they are quite negligible and can be neglected. So we have used 0th order and 1st order terms, and we are getting the solutions as like this: the 1st order solutions and 0th order solutions given by theta 10, theta 20, and theta 30 for region 1, region 2, and region 3.
Okay, you say that this is the exact solution by applying perturbation method to your
yes, sir.
systems. Okay.
Yes.
Thank you so much.
Yes, sir. Yes, sir. Okay, sir. Thank you. Welcome, sir.
If you go for analytical solutions,
Only first order, the calculations are very lengthy. So what I have done is in MATLAB,
Yes.
in MATLAB,
Yes.
I have created a series. Up to 25, 26 terms, we can find the solution. Even then, the solutions are approximate. They are not exact.
Thank you so much.
Yeah. Okay. That point I wanted to make you clear.
Okay, perfect. No, thank you very much. Thank you very much, everyone, esteemed guests, colleagues, and thank you to the Scientific Guild here, the Global Scientific Guild, for this opportunity. So today I'll more applied than some of the presentations that we've been seeing here today. So in terms of a presentation outline, I'll be talking about just the background, what distributed optical sensing is, tell you a little bit about who we are, and the development of the techniques in terms of laboratory testing, and then some in situ results, and some other themes that are related to distributed optical sensing. And so where we are in Canada here, some of you may not be familiar, as we have a global viewership here. So this is Canada. And if we were to look in the eastern, southernmost part in the province of Ontario here, you'll find Kingston right there on the top of Lake Ontario, where the St. Lawrence River just begins. So that's where we're located. And here's our campus itself in Kingston, Ontario. And so we are a nationally accredited university. And in Canada, we require our officers to have university degrees. And so we're a research establishment which trains as well as educates the Canadian military officers within Canada. And here you can see some of our laboratory facilities as well within our department. And we're also very closely affiliated in Kingston, Ontario, with Queen's University, because we are the two higher learned universities within the city. And here you can see our campus. So you're all welcome to come and join us in Kingston, should you be in Canada. And so my expertise has to do with tunneling and underground excavations, as we can see here. Really the physical testing of tunnel support, as well as in situ testing. And also this presentation will focus specifically on the monitoring of geotechnical and infrastructure works using fiber optics. But we do the whole gambit in terms of taking a look at the various scales. So we'll analyze our materials at the micrometer scale, taking a look at interfaces as well as the micro mechanisms that might be in play in terms of tunnel support. And then we could do some physical testing at the millimeter and centimeter scale, as well as come up with numerical models at this scale to see how the behavior of the soil, how soil behaves due to physical testing or even excavation, as well as how does our support behave. And then we can increase the scale to the meter scale and take a look at larger support elements in the laboratory, but also test things at full scale and in situ as well. And so that full gambit of micro scale to the full scale to try to gain an appreciation of how the materials, the earth materials work or behave and their performance, as well as the performance of the support elements that we create to try to shore up these excavations. And so what's the motivation of this line of research? Well, there's larger and larger projects that are taking place in the world and we've got to meet these increasing demands for our growing population and the need for infrastructure and larger infrastructure. And we're being a little bit more robust in terms of trying to excavate in more difficult conditions. And this places challenges on supporting these types of projects. And we also need to understand these support members in order to then feed that understanding into our design, so into our codes and design manuals. So that's the motivation here. And really what we do is we've taken an engineering design approach where for a geotechnical engineer, it's determining what are the mechanics, what is the material behavior of the soil, the rock, and then trying to determine other influences in terms of stresses, orientations, or groundwater effects perhaps, and then trying to determine that ground behavior and come up with a certain support design. And so two major aspects need to be addressed here. We need to have a realistic estimate of the expected ground conditions. So we need to do a very good preliminary site investigation so that we can determine the potential behaviors as a result of that excavation. And once we understand that, then we can go into the design aspect, which is to design an economic and safe excavation and ensuing support methods for the previously determined ground behavior. So again, our research is within this type of engineering design philosophy. And really, if we take a look at Volkmann in 2003, his sentiments still echo here today, that we have this rapid increase in use of support systems, but we don't have an increased understanding of the mechanisms or the interactions between the support system and the surrounding rock mass. So we really need to kind of determine how these behave, because in the past, these were fixed by experience or an empirical approach. And so if we take a look at the International Tunneling Association, which is the main association for tunneling, we see that instrumentation and monitoring is a very key component of an observational method of how to design support, but also how to determine behavior. So we can only optimize the design if we use the data that was obtained from properly instrumented monitoring equipment. And so we can take a look here at some support that's in situ in two different realms. We have support that goes above the crown of our tunnel, these umbrella arches, which we'll talk about here, but they're about 10 to 15 meters long, 20 to 30 centimeters in diameter pipes that are installed above the excavation so we can safely excavate underneath. There's also face bolts that get put into the face of an excavation so that we can increase the amount of confinement on the face. And then shotcrete, a type of concrete that's sprayed on, we can spray on right after the excavation, we can put some shotcrete on. Also, we can put rock bolts at different spacings, different lengths into our excavation, and use steel meshes so that we can catch any fragments that might detach from the sidewalls or from the roof of our excavation as well. But if we were to take a look at kind of the ground support mechanisms, what we have here is we have rock or soil, ground, and we have an excavated face here. So we have a hole that we put in our material. And due to that, we get a loss of confinement and we get a redistribution of stresses around our periphery, around this opening. And there's all sorts of ground loads that occur and a weakened and damaged ground that ensues. And of course, there's existing structure to the rock, let's say, and those could cause a mobilization of the rock itself. Okay, so there's all sorts of things that we need to analyze. And we could use different types of technique. We can use shotcrete, like I said before, that has a retaining function here to be able to mitigate the amount of movement. We can put in rock bolts, which then go into the periphery of our excavation to try to hold into the more competent rock here, and then try to mitigate, again, the amount of displacements that we have within our excavation, because we need to meet a certain amount of dimensions, a certain minimum threshold for the railway or the vehicles that need to pass through this particular opening, or even in a mining scenario to make sure that we have the opening that's required. And so there's all sorts of mechanisms that are in play here, and we have to make sure that we keep safety in mind during each of the excavation steps. And we can also have not only the hold function here, but we could also have a reinforce function of our rock bolt here, where if these ground stresses then mobilize along this existing fracture here, well, then this also reinforces the rock mass itself. And we can see certain amount of failures that have occurred within examples around the world from excavations. So here we have a significant amount of roof failure that went into the opening. Okay. And then here we have a certain amount of squeezing or deformation of our material. So we should have an opening here, but it has come in on itself. And now the opening is a lot smaller than the envisioned design specifications. And historically, what we can do is we can monitor usually the inside of the face itself and try to infer what's happening past the face or past the sidewalls or past the roof into the rock mass. So we have an excavated face, and we can either survey and determine if there's a certain amount of displacements using survey targets, or we could use LiDAR to be able to do a three-dimensional scan and do successive scans whereby we can scan once, scan again, and figure out the difference between the two scans. And so we infer what kind of stresses caused that amount of displacement. And if we were to take a look at a live mine and see some of the rock bolts that have failed, we can see that there are mechanisms that are definitely at play. We can see that there's a bending function here, and we can also see that there's a stretching component here. So there's a coaxial stress, axial because the force that caused this was in the direction of the rock bolt itself, and then a bending that occurs. And so there's multiple mechanisms that are at play here. And if we were to take a look at historic ground monitoring, usually what happens is that we could have maybe 1 point monitor here. So historically, we have a load cell that's attached to a rock bolt or some type of rock support. And because this is being pulled on or pushed upon by the rock itself, we get a certain amount of load that we can know that this entire element is under. Okay, but we don't know the distribution. We just know that load. And so to be able to try to address this, others have put in, let's say, strain gauges at multiple discrete points across the rock bolt or support. And so now we could figure out at these particular locations what type of strain is occurring here and infer the amount of stress. And then here to address, let's say, not only determining at 1 point, specific point where that load is, or what that displacement is, others have come up with discrete measurement zones between different elements. We have, and we can determine the long base length strain across that support element. So historically, this is how discrete ground monitoring occurred. And again, we have these mechanisms that are in play, and at discrete locations, you might not be able to pick out this entire profile. Or if you have a rock bolt, and you can see a rock bolt that's embedded here that was inserted, the original borehole trace is here in the dotted line. You can see that it has displaced as well as bent. So there's a shear discontinuity there, and you've got a certain amount of movement and displacement that has occurred. And so if we were to take a look at these discrete locations, let's take a look at what could be captured, because usually in the field, what we do is we make assessments based on what we see in the field, what we see from the data that's recorded. So if I had a spacing, let's say 40 centimeters between my two support or correction, my two discrete monitoring locations, this is the distance along the bolt, and this is the amount of strain. This will pick up a certain amount of strain, and at this location will pick up a certain amount of strain, but we can't really infer anything other than what we see here, but we don't know what mechanisms might be at play. If we were to increase the amount of sensors that we have, thereby decreasing the amount of length between the two sensors, then we can pick up and have a more characteristic strain profile along this support element. And if we were to kind of increase again the amount of sensors and decrease, we can get a certain amount of strain profile across here. But if we were to use distributed fiber optics that we've developed at RMC in our lab, we can see here at every 0.65 millimeters along the entire length, we can see what the strain profile is. And we can see here that there's a two-way shear profile that is occurring at these locations and this location here. So that's a lot better than what we've seen before with less monitoring locations. And we knew that from the beginning because we took a threaded rod, we instrumented it with fiber optic, and then we put it through a machine or through an apparatus here where we have two fixed ends on the blocks, and the middle block is allowed to move at certain loads. And so along these peripheries, these boundaries here, we can see that there's shear, and we can pick it up clearly. So again, the difference between historically having discrete locations here and making design decisions based on this is uniquely different than being able to determine what the strain profile is across the entire support element at 0.65 millimeters spacing. And we can see the unique behavior. Okay, now we can make design decisions. So this is what we're bringing to the table in terms of our technique. So what is this technique? Well, it uses a standard telecom fiber optic, and the sensor output diameter is less than 0.25 millimeters. It's based on backscatter. So it's a specific type of fiber optic technique. There are others. It's intrinsically safe and immune to EMI, so electromagnetic, different types of inputs, and very low signal loss along the ends. And you've got a strain sensing range of 15,000 micro strain. And in our lab, we've been able to record 25,000 micro strain. And we could bring it into the field and protect our unit here. And so we can see some details here of the fiber optic. There's a fiber optic connector, and we can see just some of the details here of a buffer coating on the fiber optic itself, another protective coating, and then the cable jacket. And what we've been able to do is take a rebar and be able to put in grooves on diametrically opposed sides. We machine them into the rebar. And what we do is we put the fiber optic at one side and we put it in the groove, and then we loop it around, and then we put it on the other side. So we're able to get the sensing length at one side of our support and the other. You can see here the machine, you can see a fiber optic, and then we encapsulate it using an epoxy resin. And here you can see some more details of this. And in this particular example, we see a number 6 grade 60 rebar specimen. So a rebar that's used as a rock bolt. So the fiber optic is coupled with the steel using a metal bonding adhesive. And we've played with a lot of different adhesives as well within our lab. And we also use a lot of conventional instrumentation as well to make sure that we have redundancy in our readings and we can prove the concept that fiber optics and what we're reading is something that's feasible. Okay, here we can see one of these 4-pole specimens that we talked about. We had fixed a strain gauge to them. Here you can see one pull-out test. So we've got a rebar that's placed into a block of concrete which simulates rock, and then we have a grouted. It's grouted into a borehole, and grout is placed in there, and then we're able to pull it out, and we can see that this is again an optically looped instrument across its 2 lengths. And this is another setup here of our lab. We've got the Luna fiber optic system here, which is our analyzer. We have our frame in terms of our actuator and frame data acquisition system for the conventional instrumentation that we utilize. And then we've got strain gauges on our specimens. And here we've got a specimen in concrete again that has been grooved into a borehole, grouted into a borehole, and then our rebar that's embedded in it. And so the actuator is placed on top and then pulls on this particular unit so that we have axial loading. And here you can see some of those details as well. For a rebar bolt, we have a cementitious grout that we use, and we've got a concrete cylinder of 35 MPa that was used in this particular example, and a 31 millimeter borehole diameter. So again, this is very controlled testing, and we can pull out the specimen itself. And so what we see here is we see the actual results from the fiber optic. And we can see that we've got within the specimen itself, we have this profile in terms of strain and distance along the fiber optic. And if we were to look at just this particular section, we can see it off here to the right. And we can see the amount of strain in terms of microstrain for the various loadings that we have. And we can determine things like embedment length. How long do these rebars need to be in terms of support, so that we can see that it's not, this load is not fully mobilized within the rock itself, or in this case, the concrete, which is an important stipulation when trying to optimize these systems. How long should a rebar be within a tunneling situation over kilometers in length? And if we were to take a look at the nuances here, or the rhythmic periodic disturbances, these match where the grooves are on the rebar. This is the fidelity that we're talking about in terms of the actual response of the testing. And so it's very good technique to determine, again, the gap that Volkmann talked about, the micro mechanisms that are at play between the rock and the grout and our steel. And it's so sensitive that we inspected in this particular test, we had an anomaly at this location here from our fiber optic test. And when we did forensics after testing, we saw that there was a void. There was a grout void within the grout itself, and that's what it picked up. So again, we could use this for quality control purposes as well. And we've tested this on an assortment of different types of testing support elements. So rebars, strand cables, CT bolts, D bolts, industry standard bolts for rock bolts for tunneling and mining. And it's nice that we were able to get good results in the lab, but we also have to make sure that for practitioners, we can get useful results in the field, in field conditions. And so once we had a proof of concept in the laboratory, we had in situ testing. And here we can see hand installations. It had to survive hand installation protocols, as well installation using an automated bolting jumbo, as we can see here. So we have these mechanisms that drill and emplace rock bolts, and we need to make sure that our testing mechanisms survive that installation procedure. And here we can see some of the details associated with a pull-out test that was done. So we installed it using a hydraulic, one of these booms here, the extension booms, and then we did a pull-out test. And what happened was we had an applied load and a displacement. We loaded it up, we pulled on our rebar. Our rebar is in the rock, and we have this hydraulic cylinder, which is pulling it out across a reaction frame here. So we had a loading and an unloading cycle, another loading and unloading cycle, and another loading and unloading cycle. And we can see here that as we are applying the load during our load and unload, in this case, we have our applied load, and you can see the load increasing here. We can see the increasing of the load across the length of the rebar here. And at some point here, we go to an applied load of 100K kilonewtons, and we can determine what the critical embedment length is, which is very important, which again, it's one of the first times that we can see explicitly what's happening inside this type of system, this bolt system, bolt grout rock system. Okay? Because if we don't need to make a rock bolt so long, we could save a lot of money. We could save a lot of time in the installation as well. And so we also were able to install in another location in Edmonton, which is in the center of Canada, Western Canada here in Edmonton, Alberta. And we installed something called spiles, which again are these 3-meter length, 20 meters advanced spiles, pipes, if you will, at the top of the excavation in order to address settling issues, as well as to provide a good working environment underneath. And so if we were to take a look at some of these details, we can see the installation of these spiles. These are the spile couplings, these self-threaded drilling mechanisms. And then we had to come up with a unique technique to be able to connect through the spiles and then survive the installation here. And so this is what it looks like diagrammatically. If we were to have the opening or the periphery here, the tunnel advance here, it looks like this. It's a spile, which is, again, installed longitudinally along the direction of tunnel advance above the crown of our excavation. And if we were to take a look at the excavation itself, this is the process of drilling and putting one of these in. So again, this self-drilling spile installation procedure is something that your instrumentation needs to survive. And if we were to take a look at the successive installation, so we have here an excavation, it gets excavated a certain amount, and then a girder gets placed in place to support the opening, and then we excavate again, and then we can another advance, and we can see along the instrumented spile the actual profile of the spile between its first installation and then what is the behavior of our spile due to another advance of excavation of the face, because we need to excavate this sequentially to be able to make our tunnel opening. And so after 2 meters of advance, again, we can see the moment-induced strains here and the distance along the spiles themselves. So again, in real time, we can make some design decisions using an observational method to this technique. Again, an insight that was not, that we didn't have in the past using traditional techniques. So in conclusion, an optical sensing technique has been developed for rock support members in the laboratory and tested in situ, and with an unparalleled resolution and accuracy. And the optical solution can be realized as a novel monitoring tool with the capability to see and sense the ground. So again, if the ground was to move, we'd be able to sense that as well ahead of the excavation phase. And we're capturing thousands of strain measurements across the support elements. And we're able to distinguish between coaxial and traverse strain components. And this has been published on before within our group. And then we can determine the true strain along the element, regardless of the instrumentation orientation. We can also determine and capture complex support mechanisms, and we can apply these to a variety of construction sites as well. So I'd like to acknowledge the industrial collaborators as well as the funding support for this particular line of research, as well as the people, because at the end of the day, it's the people that help drive a lot of the ingenuity within this research endeavor. And with that, thank you very much. I thank you for your kind attention.
Yes, thank you, Professor Nicholas, for your valuable presentation. We are open to questions. Does anybody has question for Professor Nicholas?
Hi everyone. Yeah. Good morning. Yeah, according to our time here in Toronto, it's 10 a.m. Actually. Yeah. So thank you. First of all, I would like to thank you for the opportunity to present my work, and I would like to start by introducing myself and my institute. My name is Al-Sayed Mahmoud. I'm a professor of computer science at the Faculty of Applied Science and Technology at Sheridan College. If I would like just to give a quick information about the Sheridan College. It's one of the Ontario leading post-secondary institutes in Canada. If you want to know the location, we have 3 campuses, one in Brampton, Mississauga, Oakville, which are close to Toronto, and we are also close to Lake Ontario. If you see this, these are the campuses. The number of the students, we have around 500 full-time students, and you are welcome to visit this webpage and know more about the college and the institute. We have 5 research centers, excellence centers. I'm working in one. It's called Mobile Innovation Research Center. We focus on the artificial intelligence, data mining, business analytics. Okay, so for the presentation today, actually, this presentation today, I will present it looks like an overview of using the artificial intelligence in transportation. Actually, I have one of the work that I will present today. It's my work. It has been completed by my undergraduate student, and that was his graduation project or graduation thesis. But all the work here is not my work. This looks like a literature review for the using the artificial intelligence in the transportation. And one of the papers that I will present it's mine. Just only one, but I will present many papers to present it's like an overview or a literature review for the artificial intelligence in transportation. What we will do exactly here in this presentation, I will focus on the techniques and applications in the space of the transportation. And for sure, I will present the techniques very briefly and to make it easy, not specialized. So the presentation itself is designed to be like big parts, big 4 parts. The first part, it will be like a generic introduction. Then I will present the AI techniques which will be used. Then I will focus on the applications. Then we will discuss the conclusion. Okay. So here, again, what's the purpose exactly? We need to determine what's the purpose of this presentation. So I would like to present the AI-based application for doing the following: for planning, designing, and controlling transportation network structure. This presentation, actually, we will focus on how to use, to be more specific, how to use the machine learning, image processing, and optimization techniques for automatic incident detection, traffic flow prediction, intelligent transportation system, ITS. That will be the focus. So the focus here is showing the role of machine learning or artificial intelligence generally, but we will focus on the machine learning models and optimization. And definitely that will include the image processing. So as what's the AI? It's a broad area of computer science. And if you see here that the AI started in, like, you can see before 1960, there was no actually AI, because there was like a lack of technology. But between 1960 and 70, they have like knowledge-based systems, and the artificial neural network started to be seen there. However, the following 10 years, the AI research diminished or reduced due to limited applications and the data, because at that time, the scientists, they were not able to find enough data or even applications for the artificial intelligence. But starting from 1980 to 2000, the researchers, they published the back propagation and many other techniques which improve the performance of the AI algorithms. And specifically, they improved the prediction accuracy, or they minimize the error of the prediction. And from 2000 to 2020, we have like the deep learning. We have the convolutional neural network, which is like it's an extension or a new version of the artificial intelligence, but with more layers. They added more layers to this to improve the accuracy and the prediction. Okay, so right now, what are the challenges in the transportation system that the AI could help in overcome those challenges? Number one, increasing travel demand, the CO emission, the CO2 emissions, the safety concerns, the environment degradation. But the main question, why do we believe that the artificial intelligence can help in that? Actually, the availability of a huge amount of data due to the sensors. Now you know that, all of us know that there are many sensors everywhere in each road, and these sensors working 24 hours collecting information, and we can use this information and build models to predict the future, or to use it to design the network, the road network, or the transportation network. Another factor, actually, as I told you in the previous slide, the great progress, or the progress in the AI techniques for learning from data. Yeah, because that was like, it's amazing, because right now the artificial intelligence model became more and more accurate in predicting, in identifying pattern. And combined with this, actually, we had like also techniques like genetic algorithms or optimization techniques, because always, I'm pretty sure that all of you are aware of that, the trade-off or the multi-objective problems. When you have two objectives, I mean two conflicting objectives. So for example, if we would like to increase or improve the traffic in the roads, That's will require cost. You need to build more roads, wider, something like that. But there is, so this is like two conflicting objectives. If I would like to minimize the cost but improve the traffic, those are two conflicting. So we can use the artificial intelligence to model it and predict and provide the best solution. But this will not be the best, because also we would like to have something like the cost should be reasonable. So that's why the optimization techniques, which is also part of the artificial intelligence, like genetic algorithm, this is another factor. So the two main factors that motivate using the AI for transportation: number one, the availability of the data; number two, the availability of the artificial intelligence techniques that enable or facilitate identifying the pattern or predicting the future, and also the optimization for conflicting, especially for conflicting objectives. The motivations also came from the application itself. The other two factors, that was like for the techniques, because we have motivations from the techniques, the improvement in the technique, the availability of the data, but we have a motivation came from the application itself, from the transportation. We have like steady growth of the traffic. That's everywhere. You see here in the images, like this, you can see how many cars there are here. And also there is a high cost of the congestion, so, or the blockage in the roads. And you have here a number. It's for Toronto, for example, it's like $6 billion a year. That's a cost, because if the roads is blocked because of the traffic, that's definitely the city or the business will have like a cost. And actually the traditional methods cannot model and predict the traffic pattern because, or the travel patterns, because it's so complex for those traditional methods. So actually in this work here, it's like overview. I just will present what are the techniques we use, and I will present some of the papers and the achievement in that direction. So here are like examples of the AI methods we used it. As I said, we have like two main models or types of methods. The first method is modeling. We want to simulate, to model it for the purpose of the prediction. The second thing is the optimization, because when we have multiple objectives, we need to determine exactly what are the point or the setting at which we will have the best solution, which will meet the two conflicting objectives. That's what we are looking for. So for the modeling, actually, we use the artificial neural network most of the time. That's based on my review. Most of the time, they are based in artificial neural network. There are equivalent or other techniques like support vector machines might be equivalent, but in this area specifically in the transportation, most of the papers that I have reviewed, they focus on artificial neural network, and they use the artificial neural network for route planning. Yeah, for route planning. So when they design the routes, they might need to predict the future to identify what's the best design for that. And also they use the artificial neural network for incident detection. If they would like to detect if there is incident on the roads, you know that especially we have many cameras, sensors, and that stuff. So that's just example I'm giving to you about what are the methods we are used and what are the applications for we use these methods for, but later we will provide more details. And the other thing is optimization. The methods of the optimization, as I explained, the multi-objective, when we have multi-objectives, especially the conflicting objectives. I don't speak about the objectives which we can achieve both together, but the conflicting one. If we improve one objective, then the other one will be reduced, or we will not be able to optimize it at the same time. So that's why we will not, there is no way to, it's trade-off. There is a trade-off. There is no way to find the optimal solution. And the solution at that time, we need to find the near optimal solution. And for that, we have several techniques in artificial intelligence which could help us to identify the near optimal solution. So one of these techniques is the genetic algorithm and simulated analytic. These two techniques are optimization techniques based on the artificial intelligence. And for example, the genetic algorithm, they are trying to mimic the genetic and the evolution system, the genes and the evolution system. So they consider that each solution looks like a gene or a chromosome, a set of chromosomes, and they represent each factor like an item or a field of the data of this gene. Then they create a population of the genes. Then every time they evaluate it, we will explain more details about this. So, but this is one of the so why they are using the genetic algorithm of this optimization for the design, the network design, the transportation network design. Another technique is like the fuzzy logic models. The fuzzy logic models actually they used in the shortest path optimization. Everything here in this slide based on my review for the recent papers in the last 10 years. Okay, so also we have another technique for optimization like agent-based software engineering that's used for shortest path through the formulation of multi-criteria. Here, there is a drawing here. Actually, I would like just to clarify it. This shape, you can see data mining, big data, databases, machine learning pattern, and you can see the circle. It's like an overlap because this is in the area. The people just think about the AI. What's the AI? The AI actually is a very broad area. You can see here, there is an overlap and intersection of the AI with the pattern recognition. Pattern recognition is like a separate area from the AI, but you can see it in blue here. And the machine learning is another area, and the data mining is a third one. But you can see the AI intersect with most of them, and even with statistics. So the statistics and the big data for sure. But the AI will contribute to all of those. That's why I used AI, because for transportation, definitely we will need to use the big data, statistics, data mining, machine learning. That's why I used the AI, because we use different techniques from different areas. So this is like hopefully that's I don't want to go deep in explaining the techniques itself. So yeah. So we started in covering some of the techniques. As I said, artificial neural network is a famous technique. It's used for modeling the data that you collected. You would like to build a model which will simulate the traffic or simulate what you want to predict. So the idea here is just like, as I said, they are trying to mimic what's happening in our brains, though they have like many neurons. So each circle here in the neural network represents a neuron. Then that's the input. And we have like a weight here. And actually, this neural network represent like like an equation, like y, this is the outcome, the y, a1, x1. You can see if we have two inputs like x1 and x2, and this is the output, the y, and we have a set of functions and weights. So the idea here, if we collect information and we present the data as input to the neural network, and we have an algorithm, and this algorithm will update or change the weights and the functions automatically until reach the output. Because we know when we collect the information from the field, we know the input and we know the output. So the only unknowns here are just the weights. So based on the historical data or the collected data, we will change the weights until reach until we find that the output from the network matches the output, the real output. That means this network now, or this model now, exactly or represent or model the reality of the real situation. Then we will be able to use it for any future data. So if we assume like any future data, we can increase the factors, then we will get, we will be able to predict it with a good accuracy. And as I said, the artificial neural network was like, there was like a significant improvement when they invented the backpropagation. And the backpropagation is just like getting the output of the network, compare it to the real value of that input, which have been measured from the field, and the difference, they use the difference to update the weight. That means we are going towards the right model, and that was like a significant improvement. So the second technique that I would like also to give a brief description for it, it's the genetic algorithm. It solves complex optimization problems. And again, if I would like to say optimization problems, I refer to a problem with two conflicting objectives, which is like every problem like that. Because when you try, there is always a trade-off when you try to improve a specific argument or a specific factor, the other, or a specific outcome, the other outcome will be decreased or will be because you need to pay a cost for that. So we are searching these techniques help us to find a near optimal point. It's a good tool for the network design. And as I give you a very brief description for it, because you can see here in this drawing, so you can see that we have a population of a solution. So you can see each solution here, we represented like a gene, and this gene consists of chromosomes. So you can see like different colors. And for example, for the road here, that like the width of the road, the number of the cameras, any factors you want to study, you can represent the solution here of your design. So each one here, its line here represent one solution. This is a population of solutions. So we will evaluate each solution, evaluate it, give it a score. Then we have like a fitness value. Evaluate each solution based on these two factors, two conflicting factors. Then for sure, we need to pick the ones with highest score. So we will pick the ones with the highest score. Then, for example, if we start with 100 solution, then we find we have like 20 or 30 or 40 better. So we will take the highest 50. Then we can generate another random solutions. Then we evaluate it and so on. And we have several techniques to generate new individuals, because each individual solution, we call it individual. So we can have like the mutation, the crossover, that's techniques. It simulates actually the evolution system, like the human being, because yeah, that's a technique for the optimization. Then the third thing that I would like to present to, which is So far, in terms of the techniques, we highlight the artificial neural network, the genetic algorithms for optimization, and also we shouldn't forget the big data, because this is one of the challenges, because we have many sensors that collect data, and the data will be big. So what's the big data? Oh, that's a definition. It's obvious and clear. Any data, we cannot process it. So for example, we could have a file and you cannot open this file in your Microsoft Excel, or even the Windows, Microsoft Windows, your operating system will not be able to handle this file or open it, okay, or manipulate it. So that's why you need a different system. So we have big data tools like Hadoop, MapReduce. These technologies are available now and we can use it for very large. And actually the definition of the big data is like more than the volume. It's not only the volume. We have like something called 3 V's: the volume, the variety, and the velocity. The volume, that's the size of the data. If you have 1 tera data, 1 file, 1 tera, 2 tera, that's a variety. That means different formats. Velocity, that means the rate at which you receive the data. That's another thing. So what are the types of the analysis? We can do it. We have 3 types of the analysis. We can do it for the transportation, or they already used there. I'm still, if you see here, I'm still explaining about the techniques. So these are the analysis techniques, and those are the 3 categories of the techniques that we use the AI for it. The first one is just descriptive. The type of the question that we can answer is what happened, what's happening. What are the methods? We can use like business report, dashboard, score, data warehousing. And the outcome of this type of analysis, the first one, the descriptive analysis, it's well-defined business problem. So when we have the problem at the beginning, we collect some information, create some reports. This is like a descriptive, okay? We might use statistics, something like that. So then the second type of the analysis is the predictive. In the predictive, we are trying to answer a question like, what will happen? So for example, what will happen if we increase the number of the roads, increase the wide, something like that, doing something in our transportation network design. So what will happen? So we need to have like a predictive model. And what techniques that we can use for this predictive model, like data mining, like machine learning, text mining, web data mining, forecasting. And the outcome of this, the outcome is accurate projections of the future event and outcome, which will help us to reach a better design. So the descriptive, that perspective, that's the third type of analysis. It should answer a question like, what should I do? Why should I do it? And that's using the optimization techniques, which already. Okay, so we have like different applications. Do we have a specific time limit? So I need to finish the presentation. Any?
Can you please complete quickly if possible?
Yes. Okay, for sure. That's good. Okay, thank you very much. So the terms of the application is like we have like many, yeah, in many cases the traditional methods will not be able to help us. One of the things like examples of the applications like detecting traffic incident automatically or automatic number recognition. I think like that's one of the things you can, if you are able to see it, like you can see here the number, that's the number of the plate number. It's automatically detected, as you see here. So that's something, yeah. That's one of the applications here. Another application, like if we would like to add more infrastructure, if we would like to extend the lane width, so we can also using plan or design or in the control. So we always for the network design problem.
No problem. Please take your time and continue.
Yeah. Okay. All right. Okay, for the network design problem, we use that like the optimization techniques here. Like I in the literature review or in the paper, they used the simulated analytic against the genetic algorithms to improve the design of the routes. When we say the design optimization, sometimes it's like what they need to decide. Is it better to make the road wider, or it's better to design or add a new road, different place? So this is like an optimization problem. Which one will be better? Because it's related to the cost and the traffic. So we need to build a model and optimize it, determine which solution will be better. So what they did, they used in the literature, they used like a simulated analytic and genetic algorithm. They want to compare both of them. And actually the two techniques of the optimization, both of them have worked, but the simulated analytic was like more efficient, provide the results faster. But the genetic algorithms was slower, but provide better solutions or more optimal solutions. The safety management plan also. So that's actually, this is an actual project in Turkey, in Ankara. They have like they build 3 different models for the safety. Okay, so and they used the neural network and they used the back propagation algorithm, and they found that and also they used 3 models for the genetic algorithms to estimate the 3 variables, because the genetic algorithm can also be used for prediction. So they found that what they, in this work, in this model, they built the model to predict 3 outputs, to predict the accidents, the injury, the fatality rates. So for the system, so the result, the performance of the artificial neural network was better than the genetic algorithm in terms of the accuracy. So there is a big part, or a big category. It's called ITS, or Intelligent Transportation System. And in these systems, they are using the new artificial neural network type. It's called deep learning systems. Yeah, I don't know if you are able to watch this. Like, you can see, like here, vehicle detection. You can see this is a complete system, artificial. They can just based on the cameras, they see the speed of every car. That's like a detection here. So I will stop that. So that's and also this is everything automatic here. Okay, so also they use the genetic algorithm anti-fuzzy methods were used to control the traffic signals. So if when you change the signals, you can also use the genetic algorithm anti-fuzzy logic to control these signals to ensure that it's like best here. Okay, you can see here in this video, it will show to you if there is a congestion or a blockage, how they do it. You can see how it will explain just how the signals will be transferred to the system. You can see this is actually, they show the problem in this video. They show the problem, how much it will cost. Yeah, but everything here assumed. This is, yeah, this is the traditional ones here. you can see the issues, the CO2, and wasting the time waiting the others. They believe that if they, yeah, this is the new system now. So the traffic, you can see they have like some devices under the roads. This will collect information, and information will be collected and sent, like the number of the cars in this road. This will be sent to a device. This device will be sent to a network. That's the ITS in the back. So it will be processed by the computer, and the design, the decisions will be made based on the actual information or real-time information to find it. Sorry. Okay. So that's something. Okay. So like okay, this is the work. Also, we if you want to identify the time and the location of the traffic. So if you want to do it manually, it will take for a long time, but they use the artificial neural network for classification, because when you collect the information and image processing it, you can be able to classify it. And also there are traffic flow here. Also, the artificial intelligence can be used in the public transportation. As you see, everything like it's same idea. It's just collecting information, sending it to the center computers for processing and making the appropriate decisions for improving the traffic. And also shared mobility. Okay, so that's so. For example, sometimes we can, because you know now each car has like a computer capabilities and network, so we can share the mobility, we can share the information, we can share the Wi-Fi from, or the network or the internet from the cars themselves. We have like also the AI can improve the buses. We have like projects in Boston. That's it. It has been launched in 2014, and it will make the journeys more safe and reliable. Okay, so they used like anti-cloning algorithm. That's like the genetic algorithms for optimization, for optimizing the scheduling, the time when it will be on the station, based also in the real time traffic. Also, it changed like the GPS, and this is like just a diagram to show the component, the main component of the system used in Boston to improve the service of the buses. Okay, so that's the hardware, and you can see here the hardware and the software. They have the sensors, and everything is automatic, collecting the information about how many people waiting, collecting about the traffic, and this is a different system. It's a different system. It's similar to the one in the Boston, but this has been developed in China, and it's called iPass. That's the one. Yeah, the last application, the autonomous vehicles, the self-driving cars. Because if you put all the infrastructure and the sensors, the computer systems, that will facilitate everything to use the automatic, the autonomous vehicles, which is self-driving cars, and they are use the deep learning techniques also to communicate and predict what and control and make the decisions. Okay, and actually one of the applications that we have been built at Sheridan, it's a deep learning system to detect distracted pedestrian. So for example, the autonomous vehicle, if you have a self-driving cars, the self-driving need to be smart, because we have a camera, so the camera take pictures of the pedestrian. If there is a pedestrian, for example, he use his mobile or something like that while he's walking, then that will be so the system will predict that there might be accident, so it change his route based on those distracted or just inform the driver. That's we have been built this system and it was like successful. We have several scenarios for the definition of the distracted pedestrian, and the system successfully detected all those. What are the limitations of the AI techniques? The limitations are like the artificial neural network. For us, it looks like a black box because the algorithm itself, it will learn it, but not us. And also the computation is complex. It takes time. It's still like kind of slow. And the AI techniques are not capable for forecasting under a specific event, not unexpected event. These techniques will not help a lot. The help will be very limited. So for the future research, I think we might like we will rely on more on the deep learning, okay? And deep learning, which means like if we go back, sorry. So we will see more layers. You can see that's more layers of that. That's what we will see. That's what we will see. In conclusion, that's using the AI for transportation is useful. It's important for transporters to determine when and how to use AI. We shouldn't use the AI for every event or for every practice. There, we need to determine exactly when we need to use it to make rapid improvement in the blockage of the roads and making travel time more reliable and faster. These are the references, and thank you very much. And my apologies for taking more time. Thank you.
Professor Mohammed, thank you for your valuable presentation.
You're very welcome.
The solution. I will talk today about the solution to the Navier-Stokes problem. I will formulate the problem so that I hope it will be understandable for wide audience, and I will give references in which my theory is presented. Now, here is, well, it's not going. I cannot move the screen. I asked long ago that the technical person should help to see whether everything is okay. How do I move the screen?
Just scroll down your screen. Scroll it down.
Okay.
Yes.
Now, in this abstract, I explain the basic result. The goal of this talk is to show that the Navier-Stokes problem, which was originally formulated by Claude Navier in 1822, is contradictory in the following sense. If you assume that the initial data is not identically equal to 0, for simplicity, I assume that the exterior force F is 0. And if the solution to this problem exists for all T non-negative, then I prove that, in fact, U at x0, the initial data, is equal to 0. This paradox, I call it the NSP paradox, NSP for Navier-Stokes problem, shows that the NSP is not a correct description of the fluid mechanics problem for viscous incompressible fluid, and that the NSP does not have a solution. This result solves one of the millennium problem. In the exceptional case, when the data are equal to 0, the solution U exists for all t and is equal to 0. Now, two people, Claude Louis Navier and George Gabriel Stokes, are associated with the Navier-Stokes problem and Navier-Stokes equation. Now, the Navier-Stokes problem is presented here. It consists of solving this partial differential equation. U is the velocity vector. This is a necessary condition for U to hold, and this is the initial condition. F is the exterior force, P is the pressure. I assume that the liquid is of constant density, which I take to be 1. Now, this is notation that I just mentioned, and U and V will be assumed real valued function. This is the norm, L2 norm of U. The integral without limit will be integral over R3. Prime, where it's, you see it, will be the derivative with respect to t. U tilde is the Fourier transform. This is the definition I use. And this is Parseval identity for this definition of the Fourier transform. I will use in several places these two formulas, which are easy to. By C, I will denote various positive constants not depending on T or X. What I prove is that U belongs to W, which is this space. H1 is the standard Sobolev space. And this estimate, the basic a priori estimate, holds where C is a positive constant which depends on the data only. The data are F and U naught. My basic assumption is this. Now, here are the notations are repeated, so I will not go through this again. Now, the first a priori estimate. The first a priori estimate is this, estimate 4. It holds under the assumption A that I formulated. Roughly speaking, you may think that the exterior force is 0 and the initial data are smooth and rapidly decaying, both as functions of X and T. Now, a sketch of proof of this, actually it's a complete proof. If you multiply this equation by U and then integrate by parts, then you get this inequality. And from this inequality, you derive the desired estimate. Here are some details. This integral is 0 because uj point j, it's nabla c dot u is 0. This is non-negative integral, and this again, this term uj comma m uj is the m's derivative, the derivative with respect to xm of uj square over 2, and then you put the derivative integrating by parts on um, and comma m is 0 by basic assumption. So you get the following estimate, and integrating it and using the basic assumption A, you see that the desired inequality is proved. And inequality is proved by the Parseval identity. Now, my goals are to prove that the NSP is contradictory, so it's physically and mathematically not correct, and that NSP does not have a solution on the whole positive semi-axis of time axis. So first I prove theorem A. Theorem A says that if assumption A holds, then this a priori estimate holds. Now, the first part of this estimate is already proved. So the basic novel part is to prove that this quantity is bounded. What are the steps in the proof of this theorem? First, I derive the integral equations equivalent to the Navier-Stokes problem. Then for this function b of t, which is L2 norm of this, I prove this inequality. You see here the divergent classically integral. So I will need to define its meaning and to prove some mathematical results about it. And I consider this integral equation, which is related to this inequality, and I prove that the solution, any positive solution to this inequality, satisfies this estimate, where Q is the solution to this integral equation with divergent classically highly singular kernel. From this inequality, I derive the NSP paradox that I formulated. Now, there is a large literature on Navier-Stokes equations. From 1822, it's about 200 years. There is no way for me to discuss the literature here. I will mention only the book by Ladizhinskaya. The integral equations equivalent to the Navier-Stokes problem is equation 7, where F capital is the data and it's defined by this relation. for simplicity and without loss of generality, I assume that F, the exterior force, this F, is 0, and then F capital is given by this integral. G here is the tensor that is explicitly calculated in my book 1. The references will be shown later, and it's given explicitly by this formula, where this quantity is the Fourier transform of G. Clearly, the Fourier transform is satisfying this inequality. G is the solution to this problem. This is a divergence of G is 0, and PM is P, the pressure, times EM. EM is the orthogonal basis in three-dimensional space. Now, if you transform by Fourier this equation in equivalent to the Navier-Stokes problem, then you will get this integral equation where this bold star denotes the convolution in R3. Now, I note these quantities. The estimate for the Fourier transform I already mentioned, and the estimate and the relation of the formula for the Fourier transform of G small, which is the heat equation kernel, is a given, it's known. Now, from the Cauchy estimate, I derive this inequality. So let us derive this inequality where B is this quantity. If I take the integral equation, the Fourier transform of 7, let me show you this integral equation, and take absolute value of both sides, then I will get this inequality. All quantities here are positive. Then I multiply this by absolute value of Xi and take the L2 norm of both sides. The result is this inequality if I take into account this formula, which I already showed you earlier. Now, B naught here is this. It depends only on the data. Now, with the inequality I just derived, I associate this integral equation. You see that kernel here is highly singular. The integral diverges if understood classically, no matter how smooth and rapidly decaying Q is. So both equations, 14 inequality and 15 integral equation, are equations with highly singular kernel. I must define these integrals and derive consequences from these. The basic consequence I need is this inequality. Why? Because I solve this integral equation explicitly in a space that will be specified. And I prove that if the initial data are smooth and rapidly decaying, then Q at 0 must be 0. This is the theory to define the integrals, the convolutions, these convolutions with singular functions. I do it in this talk using the Laplace transform. This is the Laplace transform. And let's define the function phi lambda. T here and everywhere below is what is usually defined as T plus, the function which vanish for T negative. But for writing purposes, I will just write T. So the convolution in phi lambda and B is this integral. For lambda positive, it's defined classically. The Laplace transform of this I will show you in the next slide. And I will define this convolution for lambda negative, namely since the power here that I use is -5 divided by 4. My lambda is -1/4. So the integral inequality can be written in this form, where C1 is positive constant, which is explicitly given. Gamma here is a gamma function. And the integral equation for Q is 18. It's given here. Now, the Laplace transform of this convolution is defined classically for real lambda positive. For real lambda negative, it is understood and defined as analytic continuation with respect to this parameter lambda, complex lambda. I have this formula. The Laplace transform of phi lambda is equal to this quantity, and it's valid for all complex lambda. For lambda positive or real lambda positive, it's understood classically and valid classically, and otherwise it's valid for analytic continuation for any complex lambda, because the function p to the power of minus lambda is an entire function of lambda for any positive p. So this quantity with singular integral is defined by this expression. P to the power of 1/4 times L of B is the Laplace transform of this quantity. L minus 1 is the inverse Laplace transform. Laplace transform is injective on any domain of its definition. And I will specifically show you that this function under assumptions that I will make, namely the data are smooth and rapidly decaying, makes sense, and L minus 1 is a continuous function, and this function vanishes at t equal to 0. Now, since this is a principal point, let me explain a little bit what is the Laplace transform of t to the power of lambda minus 1, namely this integral. For lambda positive, you calculate it easily and you get this expression where gamma is the gamma function. If you divide both sides by gamma of lambda, you will get 1 over p of lambda that I showed you. The gamma function is known to be analytic with respect to lambda on the complex plane, except for these values of lambda, at which it has simple poles. Now, to solve this integral equation, I apply the Laplace transform to both sides using the formula I showed you. And I get this formula for the Laplace transform of Q. So the unique solution to this integral equation 18 is given by this formula. I will now explain why this formula makes sense and why Q is a continuous function which vanishes at 0, provided that B naught, and that is assumed, is smooth and rapidly decaying. Now, if B naught is smooth and rapidly decaying, then for Laplace transform you have this estimate. So I check that this function, which you see here, 1 over this function, is analytic in the region realis p greater than 0, and it's bounded as a function of p and is O capital of 1 over absolute value of p to the power of 1/4 for large absolute value of p. That's not difficult to check. Now I prove the following theorem B. Theorem B, if it's proved, gives also theorem, the conclusion of theorem A. Suppose that B naught is smooth and rapidly decaying, and this number B, it has nothing to do with B of t, is greater than 1. And then L of B naught satisfying this estimate. In my case, this number is 5 divided by 4. And equation 18 is uniquely solvable in this space, continuous functions on positive semi-axis of t, and Q at 0 is 0. The conclusion of this theorem follows from lemma 1 immediately. This is lemma 1. If you assume that F capital is analytic in the region real part of P is positive, if absolute value of F of P satisfies this estimate for large P with B, this number, greater than 1, then this analytic function is a Laplace transform of F, where F is bounded, uniformly bounded on positive semi-axis, and F at 0 is 0. Now I will prove this lemma. F of t, it's can be written by this formula, by the inversion formula for the Laplace transform. The integral here converges classically because f of p is analytic and continuous up to the imaginary axis, and for large p, it decays faster than 1 over p to the power greater than 1, excuse me. Therefore, f is a continuous function satisfying this estimate. Now I prove that f at 0 is 0. Indeed, by the formula that I showed you, if you take p equal to is, so sigma 0, then f, when t equal to 0, you will get this formula. By analyticity, this quantity, which is a closed integral, it is taken over imaginary axis from minus in to in, and it's closed from the right by a semi-axis. This integral by analyticity is 0, and therefore its limit is 0. But this integral over f is in the limit equals to 0 because f of p decays faster than 1 over p to the power greater than 1 for large p. So I get that this limit is that I mentioned. I get that this limit is 0, and therefore f at 0 is 0. This yields the NSP paradox. I assumed originally that u at x0, the initial data, is not identically equal to 0. I prove a little bit later that b is not more than q, and I mentioned it already. Therefore, if q at 0 is 0, then b at 0 is 0. If b at 0 is 0, then this quantity, that's the definition of b naught, is 0, and therefore this quantity is 0. Since the initial data is assumed to be a regular function, a smooth, rapidly decaying function, this relation means that u tilde is 0, and therefore u at x0 is 0, and this means that the Navier-Stokes paradox is proved. This is the formulation of Navier-Stokes paradox as I formulated it in the abstract and in the beginning. So let us prove this inequality. B is not more than Q, B of T. I need two lemmas. First lemma, lemma 2. If you consider this operator with A, this number, greater than -1, then you consider it in this space X capital. T capital here is an arbitrary positive number. Then I claim that the spectral radius of this operator is equal to 0, and therefore this integral equation, it's a linear integral equation with respect to f, is uniquely solvable in this space by iterations. So the solution can be represented, is unique and can be represented by this series that converges in X capital. Now I sketch the proof of this lemma. The spectral radius is defined by this formula. By induction, I prove that this estimate is true, where A is this number in the definition of operator A capital. Gamma is the gamma function, and this is proved by induction. From this, it follows if you take the square root and use this known formula for the asymptotics of gamma function for large absolute value of z. The radius, spectral radius of A is 0. And then this equation, it follows from this result, can be solved uniquely by iterative process 27. This iterative process. And the formula for the solution is this. Now, I need also lemma 3, which says that this formula holds for any complex lambda and mu. And if lambda plus mu is 0, then this formula holds, where delta is the delta function. The proof is quite short in my presentation file. I take Laplace transform of this and get this, well, from this formula. Since the inverse Laplace transform of this is phi of lambda, I get the first formula. Now, if lambda plus mu is 0, then this function is equal to 1, and the inverse Laplace transform of 1 is delta. So this formula holds. Now, I will prove that B is not more than Q. We had this inequality. Apply to this inequality the operator phi 1 over 4 cross. So this means convolution. And use this relation. That's part of lemma 3. Then you will have this inequality. Note that if you apply phi lambda convolved with any lambda positive to a non-negative function, you will get non-negative function. So this operator preserves the inequality sign. Let 1 over c, c1 be denoted by c2. Then using iterations described in lemma 2, applying to this inequality, I get this formula. A similar argument for Q leaves this formula for Q. So the desired inequality is proved. This sum is not less than this B. This sum is Q. since Q at 0, as I proved, is equal to 0, it follows that B at 0 is 0. Therefore, the Navier-Stokes problem paradox is proved. Now, I prove uniqueness theorem, although it's not used in the previous arguments. It's a new theorem, and the theorem says that if uj for j equals to 1, 2 belongs to W, remember that W is the set of functions such that norm of U plus norm of nabla U is bounded by the data, bounded. So if uj solves this equation, more precisely uj Fourier transform, that's integral equation equivalent to the Navier-Stokes problem, then U1 is equal to U2. I prove that U1 tilde is equal to UT2 tilde, and that is the same as proving that U1 is equal to U2. So denote Z as the difference, U1 tilde minus U2 tilde. From this equation, subtracting equation with J equal to 1, equation with J equal to 2, I get this relation. Here I use the Cauchy inequality and the fact that this estimate is already proved and this estimate is already proved. Here there is a misprint, U1 tilde should be here. And this is okay because norm of U2 is bounded if and only if norm of U2 tilde is bounded. So I use this Cauchy estimate and get this inequality. And in a similar way, I get this inequality. Therefore, I obtain this inequality for absolute value of Z. Eta here is norm of Z plus this. Now I take norm of the previous inequality and get this inequality. Then I multiply this inequality by absolute value of C, and I get this inequality. Now I will take the Laplace transform of this and Laplace transform of this, add, and get this inequality. Now, if the Laplace transform of eta is the Laplace transform of eta is non-negative. If L of eta is non-negative, then from the previous inequality, when P, this parameter, goes to plus infinity, I will, I will get the following inequality. And that is obviously a contradiction, because for large P, it gives you this inequality. Therefore, I conclude that L of eta must be equal to 0 identically. By the injectivity of Laplace transform, it follows that eta is 0. Therefore, Z is 0. Therefore, the uniqueness theorem is proved. Now, in this book, the results that I presented are proved in detail. Mostly it's equivalence of the Navier-Stokes equation to the integral equations that I wrote, and the theory of hypersingular integrals that appear in the integral equation for Q and integral inequality for B. In this paper, this paper is very close to my presentation. In this paper, the Navier-Stokes equations paradox is presented in a short way, and the arguments are slightly different. Now, I thank you for your attention, and all questions are very welcome. In case you want to ask questions later, you can send an email to me to this email address. Again, thank you, and I am ready for your questions.
Professor,